Imagine stepping onto a spacecraft headed for Mars, already knowing you'll never return to Earth. It sounds like science fiction. But for the first humans who go there, this may be the reality. Based on what science understands today, travelling to Mars could mean giving up life on Earth forever. And the biggest obstacle isn't rockets, fuel, or technology, it's the human body. A mission to Mars pushes the human body further than anything we've ever attempted. Reaching the Moon took just 3 days. Reaching Mars takes 6 to 9 months one way. That alone changes everything. Astronauts would spend 2 to 3 years away from Earth before a return is even possible. 2 to 3 years of constant physical stress in an environment the human body was never designed for, and the distance is only the beginning. At its closest, Mars is about 55 million kilometers away. Even light takes more than 20 minutes to travel between Mars and Earth. If something goes wrong, there is no rescue, no emergency evacuation, no quick medical help. A serious medical emergency means the nearest hospital is months away. These astronauts would be completely on their own in a way no humans ever have been. But the real danger isn't the isolation or the distance, it's what happens inside the body during the journey. A Mars mission exposes the human body to 3 radically different gravity environments. First comes long-term weightlessness during the journey through space, then life on Mars where gravity is only 38% of Earth's, and finally, if a return is even attempted, a sudden reintroduction to full Earth gravity. Each transition is extreme. Experiencing all 3 over several years pushes the body into unknown territory. What scientists do know is deeply concerning. The human body is finely tuned for life on Earth. When that environment is removed for long periods of time, the body begins to adapt. Slowly at first, then more aggressively. And after a certain point, those changes stop being reversible. Astronauts who spend just 6 months on the International Space Station often need weeks before they can walk normally again. Their bones weaken, their muscles shrink, and their hearts lose strength. And this happens while Earth is always nearby, only 400 kilometers away, with rescue always possible. A Mars mission lasts far longer, and coming home may not be an option at all. In the chapters ahead, we'll look at what happens to each major system in the human body during this journey. Bones becoming fragile, muscles wasting away, hearts shrinking, eyes changing, brains taking damage. Step by step, it becomes clear why the first humans to reach Mars may not be able to return. When we imagine the dangers of a Mars mission, we often think about technical failures or asteroid impacts, but the most dangerous threat is invisible. Cosmic radiation constantly bombards astronauts in deep space, damaging their bodies at the cellular level. On Earth, we are protected. Our atmosphere and magnetic field block more than 99.9% of this radiation. In deep space, that protection is gone. Over a Mars mission, astronauts would be exposed to between 870 and 1,200 millisieverts of radiation. That's roughly 700 times more than what we experience on Earth. The equivalent of hundreds of CT scans or thousands of X-rays in just a few years. The effects are severe. Cancer risk rises dramatically. The cardiovascular system ages decades faster. The brain shows measurable cognitive decline. Memory worsens, thinking slows, decision-making becomes harder. These changes may be permanent. Cataracts can form in the eyes, and the immune system weakens as bone marrow is damaged. Even worse, shielding offers little protection. Thick layers of material can actually create secondary radiation, making the problem worse instead of better. After years of exposure, the human body is fundamentally changed. Radiation becomes the first domino in a chain reaction of damage that slowly makes a return to Earth impossible. Mars has long captured the imagination of explorers, scientists and dreamers, standing as the next great frontier for human exploration because of scientific, technological and existential reasons. The red planet symbolizes the potential to extend human presence beyond Earth and test our resilience and ingenuity on a truly alien world. First, Mars offers a compelling scientific opportunity. Its surface reveals a complex geological history, providing clues to the evolution of planets, water presence in the solar system, and possibly the origins of life. Unlike the Moon, Mars shows signs of having had liquid water, riverbeds, minerals formed in water, and underground aquifers. Discovering past or present microbial life could be revolutionary, changing our understanding of biology and the potential for extraterrestrial life. Mars's environment challenges human ingenuity. Its thin atmosphere is over 99% carbon dioxide, with little breathable oxygen. Temperatures can dip to minus 150 degrees at the poles, and dust storms can last weeks, blocking sunlight and disrupting operations. These harsh conditions act as a proving ground, pushing our technology, life support, habitats, and inspiring solutions for future colonization on less hospitable planets. Technologically, Mars is within reach. Advances in rocket propulsion, space habitats, and robotics have made crewed missions feasible. Companies like SpaceX, NASA, and others are planning missions in the coming decades. Developing reliable transportation systems to ferry humans and cargo across millions of miles has become more realistic. Innovations like reusable rockets, miniaturized life support modules, and autonomous robotic shuttles form the foundation for turning a once insurmountable challenge into a tangible goal. From a political and economic perspective, interest in Mars exploration is growing. The drive toward a multi-planetary civilization is not just about exploration, but about securing humanity's survival. Earth faces threats like climate change, nuclear risks, and asteroid impacts. A self-sustaining colony on Mars could act as a backup, protecting our civilization, culture, and biological diversity should catastrophe strike Earth. Mars also offers resources vital for sustaining human life. Its soil contains water ice, which can be converted into drinking water, oxygen, or rocket fuel through chemical processes. The planet's regolith may contain elements useful for manufacturing building materials and electronics, reducing reliance on Earth supplies. This in situ resource utilization makes establishing colonies more feasible and affordable. Beyond scientific and practical considerations, there's an intrinsic human drive to explore, an age-old quest to discover new worlds and understand our place in the universe. Mars represents the next step in this journey. Venturing onto another planet fulfills a fundamental aspect of human nature: curiosity, resilience, and the desire to expand civilization. It's about transforming the dream of exploration into reality. The cultural and inspirational impact of Mars is profound. Major missions have already ignited global interest in STEM fields. These endeavors motivate new generations to pursue science, technology, engineering, and mathematics, fueling innovation and economic growth. Reaching Mars and establishing a sustainable presence embodies purpose and unity, inspiring nations and communities to work together on a shared goal. Mars offers an environment for developing technologies that benefit Earth. Closed-loop life support, renewable energy, sustainable agriculture, and habitat engineering, pioneered in the harsh Martian environment, have direct applications on our home planet. This synergy between exploration and terrestrial solutions encourages investment, knowing innovations can also improve life on Earth. Psychologically, Mars exploration tests our ability to work under stress, adapt, and maintain mental health in extreme conditions. Long-term missions force the development of support systems, communication tools, and social structures, which are invaluable for future interstellar travel and for improving urban life here. The mental resilience and social cohesion needed for Mars missions can translate into better societal cohesion on Earth. Economic prospects are increasingly linked to Mars exploration. The idea of mining asteroids and Mars for rare metals and resources is gaining traction. While largely speculative, it highlights the potential for new industries based on off-world materials. Establishing resource extraction on Mars could revolutionize industries back home, creating new economic models and sustainable development opportunities. Countries and private companies are investing heavily in space exploration, recognizing strategic, technological, and economic advantages. The rise of commercial spaceflight has reduced costs and accelerated timelines. Companies like SpaceX and Blue Origin envision colonies that serve as launch pads for exploring moons of Jupiter and Saturn, expanding our reach into the outer solar system. Ultimately, Mars is the next frontier because it embodies humanity's desire to explore, secure our future, and push technological boundaries. It demands global cooperation, innovation, and courage, traits fundamental to our species. Mars is not only about discovering extraterrestrial life or scientific breakthroughs, it's about proving we can overcome obstacles, adapt to new environments, and forge a multi-planetary existence. The journey to Mars signifies human evolution, transforming us from a species on a single planet into explorers spreading across the solar system. As we gaze at the night sky, Mars symbolizes humanity's limitless potential, our curiosity, resilience, and hope for the future. The red planet is more than a celestial body. It's a symbol of what it means to be human, challenging us to dream bigger, reach farther, and build a legacy beyond Earth. The drive to explore and establish a presence on Mars is fueled by scientific, economic, and geopolitical motivations, each intertwining to propel humanity toward the red planet. These motivations reflect both our innate curiosity and practical aspirations to ensure a sustainable future in space. At the core of the scientific motivation is humanity's desire to understand our origins, planetary environment, and the potential for life beyond Earth. Mars is an ideal target due to its proximity, similarities to Earth, and intriguing history of climate change and geological activity. Evidence of past water flow, ancient riverbeds, mineral deposits, and possible subsurface niches where microbial life could exist or have thrived make it a key scientific focus. Unlocking these secrets offers potential discoveries on planetary formation, climate evolution, and the prevalence of life in the universe. Such revelations could deepen our understanding of biological resilience, planetary geology, and environmental fate. Searching for past or present life on Mars also seeks to determine if life exists elsewhere and whether Earth is unique. Rovers, orbiters, and future human explorers all contribute to this scientific narrative, enhancing our understanding of the universe. Additionally, studying Mars can inform climate science, planetary habitability, and atmospheric science, knowledge that can help protect Earth and other planets from environmental threats. Beyond curiosity, studying Mars has practical implications for future human habitation. By examining its geology and climate, scientists can identify resources like accessible water, suitable soil for agriculture, and potential energy sources. Water ice is especially critical because it can be converted into drinking water, oxygen, or rocket fuel, supporting sustainable habitats and reducing reliance on Earth supplies. Mars also serves as a natural laboratory for extreme environments, offering analogues for future off-world colonies or interplanetary settlements. Economic motivations are increasingly prominent, especially regarding resource extraction. Space agencies, private companies, and investors see Mars as a frontier for mining rare minerals, metals, and valuable materials. Water ice can be processed into fuel, while minerals like iron, aluminum, or precious metals could sustain industries off Earth. Space-based manufacturing, taking advantage of the low gravity, may produce new materials and innovations, making space economies more viable. Future industries might include tourism and entertainment, offering adventurous expeditions, luxury habitats, or scientific tourism. As technological capabilities for sustained Mars presence develop, habitat construction, life support, and interplanetary logistics could create markets and jobs. Turning Mars into an economic hub drives efforts to develop infrastructure, spacecraft, habitat modules, and life support systems, fostering innovation and economic growth beyond Earth. Geopolitically, the race to secure a foothold on Mars reflects larger strategic competition for influence in space. Historically, exploration has been driven by national pride and security. Consider the Cold War space race exemplified by Apollo. Today, nations invest heavily to demonstrate technological prowess and geopolitical strength through space programs. A presence on Mars can provide symbolic and strategic advantages, such as establishing extraterrestrial outposts for science, security, or resource access. Controlling Martian infrastructure and resources could influence diplomacy, fostering alliances or rivalries depending on motives. Leading nations could shape global standards on space activity, resource rights, and security protocols. Countries like the US, China, Russia, and the European Union have shown ambitions for Mars, each seeking to boost national prestige and strategic positioning. Private corporations are also vying to profit from this frontier. Visionaries like Elon Musk's SpaceX aim to develop reusable rockets, human landers, and self-sustaining colonies. Successful Mars settlements could open new markets and technologies. These ventures might influence space policy and regulation by demonstrating commercial viability, creating investor opportunities, and shaping the governance of space activities. These intertwined motives are mutually reinforcing. Scientific breakthroughs can lead to economic gains through resource discovery, while technological advances can accelerate exploration. Geopolitical competition spurs innovation, resulting in more ambitious missions. Conversely, scientific discoveries justify economic and strategic pursuits by providing evidence-based pathways for sustainable, beneficial activity on Mars. Underlying everything is an intrinsic human desire to explore the unknown, to leave a mark beyond Earth, and to secure the future of our species. Our drive to seek new horizons and transcend terrestrial limits has motivated exploration for centuries. Mars symbolizes both a formidable scientific challenge and a testament to human resilience, ingenuity, and ambition. Every mission, rover, and satellite orbiting Mars embodies this universal yearning to push boundaries. As we aim to establish a human foothold, these motivations will continue to evolve and converge, shaping a future where Mars transitions from a distant celestial body to a new chapter of human history. This convergence reflects pragmatic needs and our deep-rooted desire to understand ourselves and the universe more profoundly. Despite vast hurdles, the pursuit of Mars exemplifies our relentless spirit of discovery, curiosity, and hope, aiming to thrive beyond our home planet and forge a new chapter among the stars. Word count: exactly 871 words. When discussing travelling to Mars, it's crucial to distinguish exploration from colonization, as their implications extend beyond mere discovery. Exploration involves venturing into the unknown temporarily, driven by curiosity, scientific interest, and understanding. It means visiting a new world, conducting experiments, collecting data, testing theories, and then returning home or moving to the next target. Think of it as a scientific surveying mission. Scientists or robots land briefly, perform their tasks, gather samples, observe, and leave, knowing they aren't permanently altering the environment or society there. Colonization, by contrast, focuses on establishing a permanent self-sustaining presence. It aims to make a distant world part of human civilization, a new home with responsibilities and long-term commitments. Colonization involves building infrastructure to support human life, systems for food, water, shelter, energy, healthcare, and social and political institutions. It's about transplanting Earth's social fabric into a new environment, with the goal to remain indefinitely. Unlike exploration, which views the planet as a temporary outpost or scientific station, colonization claims permanence and a desire to thrive there as an extension of Earth. On Mars, this distinction is clear. Exploration might involve deploying robotic rovers, conducting human missions lasting weeks or months, and collecting samples for analysis back on Earth. Such endeavours are inherently limited. They don't require permanent settlements or societal development. Explorers, whether robots or humans, leave behind footprints, data, and perhaps a brief base but no lasting presence. Colonization, however, demands far more ambition. It seeks to transform Mars from a hostile, barren planet into a livable environment where humans can settle, work, and reproduce. The planet's environment is extremely harsh. Its atmosphere is mostly carbon dioxide with little oxygen. Surface radiation from cosmic rays and solar activity. Freezing temperatures, toxic soil containing perchlorates, and water, mostly in ice beneath the surface or at the poles. These challenges require advanced technology and a mindset geared toward long-term survival. Establishing a colony entails constructing habitats capable of shielding inhabitants from radiation and thermal extremes. It involves creating underground farms so astronauts can grow food, reducing reliance on resupply missions. Reliable energy sources, like nuclear or solar power, are vital for life support, manufacturing, and scientific tasks. Managing waste and maintaining psychological health are complex issues. Life on Mars would not be a short-term adventure, but a sustained commitment over years or generations. Beyond logistical hurdles, colonization has social, political, and cultural implications. A community must develop governance, laws, and social norms suited to the environment. These systems might need to differ from Earth's, adapted for isolation, limited resources, and the environment shaping human behavior. Maintaining mental health and social cohesion is critical amid loneliness and distance from Earth. The philosophical shift involved in colonization is profound. It moves from exploring for knowledge to creating a new society. Settling on Mars means becoming settlers, not just visitors. This raises ethical questions. Do humans have the right to modify the Martian environment? Should we send large groups to establish sustainable communities? These are moral debates, not just scientific challenges, defining what it means to be a multiplanetary species. Culturally, colonization differs from exploration. Exploration often involves international or agency collaborations driven by competition or pride, with fleeting contact. Colonization combines motivations into a long-term, shared effort, requiring consensus, responsibility, and a vision beyond a few missions. Settlers must think in terms of generations, not just years. Economic considerations are vital. A self-sufficient colony needs a viable economic system involving resource recycling, local industries, and possibly independence from Earth. Reducing reliance on resupply missions, lifeline dependencies, is crucial for sustainability. This involves in-situ resource utilization, extracting water from soil, producing fuel locally, and manufacturing essentials. Such tasks contrast sharply with exploration's focus on minimal infrastructure for scientific return. The physical and psychological toll differs greatly. Exploration missions sometimes include mental health support, but their temporary nature means an endpoint, probably the return home. Colonization demands resilience across decades or generations. Settlers face persistent health risks, resource scarcities, social tensions, and the psychological strain of living on an alien world. Their identity becomes intertwined with survival and societal development. Failure could end human presence on Mars. Meanings differ. Exploration involves stepping onto Mars to learn, then leaving. Colonization is about staying to build a new life. The shift from visitor to settler signifies a fundamental change in humanity's relationship with Mars. The planet stops being just a distant frontier and becomes a new world to inhabit, nurture, and develop. Exploration may involve reconnaissance, limited scientific missions, and sample return efforts. It's limited in scope, focused on understanding surface and atmosphere, with minimal permanent infrastructure. Its engagement is temporary, mainly aimed at acquiring knowledge. Colonization emphasizes long-term survival and growth. It involves creating a sustainable ecosystem where humans can live, work, and reproduce. This includes overcoming environmental challenges, building habitats, generating food and water, establishing energy sources and developing social systems, and technologies that reduce environmental hostility. Mindset shifts from short-term scientific inquiry to ongoing adaptation and resilience. In exploration, resupply missions are acceptable but limited. The main goal is data collection and sample return. In colonization, resupply alone is insufficient. Emphasis shifts to in-situ resource utilization, accessing local materials like water ice, producing fuel, and manufacturing goods to reduce dependence on Earth. Self-sufficiency and sustainability are core. The psychological implications are significant. Exploration is characterized by temporary engagement with an eventual return to Earth. Colonization demands resilience over decades and generations. Settlers face health risks, resource management challenges, social tensions, and psychological isolation. Their identity evolves from mission participants to members of a new society committed to its survival and growth. In essence, exploration revolves around discovery and understanding, temporarily entering the unknown to learn, and then leaving. Colonization involves creation and endurance, building a new society capable of thriving indefinitely. This shift redefines humanity's relationship with Mars, transforming it from a distant world to a new home to nurture and develop. The move from exploration to colonization signifies an expansion of human presence into space. It embodies technological, logistical, moral, cultural, and philosophical milestones. While exploration seeks knowledge and scientific progress, colonization aims at survival, growth, and societal development beyond Earth. The stakes are higher and visions broader, reflecting humanity's desire to forge a future among the stars. Looking back through history, explorers braving the unknown mirror, humanity's current dream of reaching Mars, uncharted territories once beckoned with promises of discovery and peril. Early explorers faced risks that seem hauntingly familiar to those dreaming of interplanetary voyages. Consider the age of exploration in the 15th and 16th centuries, marked by daring expeditions across uncharted oceans. Leaders like Columbus, Vasco da Gama, and Magellan set sail into regions where maps ended and the unknown began. Much like today's space ventures, these explorers sought new worlds, lands, and treasures that could transform their societies. But behind the excitement lurked grave dangers: treacherous waters, unpredictable weather, scurvy, and the risk of losing entire fleets to storms or hostile natives. The parallels become clear when thinking about risk management. Explorers of old knew that venturing into unfamiliar territory meant choosing between potential greatness and catastrophic failure. Columbus believed he could reach Asia by sailing west, but landed instead on an island called San Salvador. His crew's uncertainty was palpable. Could they survive the long voyage, and what awaited them? Similarly, astronauts and engineers planning for Mars must grapple with risks. Ships could be lost or damaged, rescue options limited, and failures potentially irreversible. Another chapter in exploration history that echoes today's Mars ambitions is Polynesian voyaging. Polynesian navigators, equipped with sophisticated knowledge of stars, currents, and wind, embarked on thousands-mile journeys across open ocean without modern tech. Their voyages demanded immense skill and trust in their knowledge systems. Small errors could lead to disaster. These voyages weren't just about discovery, they were about survival, knowing when to trust star maps and when to adapt to unforeseen circumstances. Today's space explorers face similar navigation challenges. Satellites and sensors serve as celestial compasses, yet uncertainties remain. Microgravity, cosmic radiation, and effects of long-term space travel on humans. Despite advanced technology, the core human challenge remains, venturing into the unknown with the understanding that not everything can be foreseen, and adaptation is crucial. The age of great expeditions in the 18th and 19th centuries offers more parallels. James Cook's voyages, or Arctic explorations, involved mapping coastlines, discovering islands and battling scurvy, unpredictable weather, and the perils of uncharted seas. Cook's meticulous planning and scientific methods moved exploration from chance to understanding and preparation. This story mirrors current space planning with an emphasis on scientific exploration and risk assessment. NASA's Apollo program, for example, was a massive undertaking with detailed planning, rigorous training, and contingency strategies. Despite the thorough preparation, the missions involved inherent risks: fire on the launch pad, astronauts stranded, equipment failures, some of which resulted in tragedy. In the context of Mars, the stakes are even higher. This isn't a 2-week journey. It's a one-way trip with no breathable atmosphere, no quick rescue, and a landscape akin to a hostile wilderness. Risks include psychological tolls, loneliness, confinement, and the impossibility of rescue if disaster strikes. Navigating these new frontiers also resembles early American frontier movements. The westward expansion epitomized the drive to push boundaries into new lands. Manifest Destiny fueled the belief that pioneers could tame the wilderness and settle vast regions. The journey was perilous. Hardship, conflict, disease, and death lurked beyond the horizon. It reminds us that pioneering always involves sacrifice. Settlers face starvation, clashes with indigenous peoples, and brutal environments. Early astronauts understood that they might not return from Mars. Courage rooted in that tradition pushes human boundaries, knowing that the journey could end in loss. The failed Arctic and Antarctic explorations underscore resilience and humility. Robert Peary and Roald Amundsen faced brutal cold, dangerous ice, and logistical nightmares. Many explorers vanished, ships crushed or lost in storms. Yet their stories highlight tenacity, the refusal to turn back despite overwhelming odds. Modern Mars missions embody this resilience. Rovers survive dust storms threatening electrical systems, cope with communication delays, and persist against adversity. Human crews will require mental toughness, rigorous training, and resilience to endure. They must persevere through extreme conditions, isolation, and the mental toll of confinement. Throughout history, exploration has been intertwined with sacrifice. Conquistadors and explorers gained knowledge, territories, and wealth, often at a heavy cost. Lives lost, cultures devastated. Polynesian, European, or polar explorers all embarked driven by curiosity and necessity, accepting high risks. Today, with Mars, the sacrifices are different but no less profound. The possibility of a one-way mission or never-returning challenges conventional notions of risk and reward. Those willing to undertake this journey push beyond safety's limits, driven by humanity's right and need to expand into space. Some parallels are drawn with Ferdinand Magellan's global circumnavigation, which faced storms, mutiny, starvation, death. His crew's resilience redefined possibilities. Today, space explorers aim to redefine human existence, understanding they step into history's pages with each move. The story of exploration teaches that progress often involves profound sacrifice and unforeseen dangers. It's about embracing uncertainty and risking everything to discover, expand, and evolve. Crossing oceans, trekking icy wilderness, or reaching for the stars, our history is woven with stories of courage, resilience, and pursuit of the unknown. Standing on the threshold of a new era, the goal of Mars, these historical parallels remind us that pushing boundaries, facing the unknown, and risking not returning are part of our quest for knowledge. It's a continuation of a centuries-old tradition, peering into the abyss, risking everything, and perhaps reshaping what it means to be human. The journey to Mars is no longer just a distant dream, but becoming a tangible reality, fueled by groundbreaking technological innovations. Each step forward depends on pushing technical boundaries. What are these innovations making a 275 million-mile voyage manageable? Let's explore the key advances transforming Mars travel from science fiction into fact. At the core of interplanetary travel is propulsion technology. Rockets designed for Mars missions have seen revolutionary improvements. Traditional chemical rockets, long used in space travel, are now being augmented or replaced by more efficient systems. Innovations like reusable launch vehicles pioneered by companies such as SpaceX have drastically cut costs and increased launch frequency. These reusable rockets, like Falcon 9, return to their launch pads after orbit, reducing expense and waste. This efficiency makes launching multiple missions to Mars feasible, paving the way for larger human endeavours. Meanwhile, nuclear thermal propulsion emerges as a game-changer. Unlike chemical rockets, nuclear thermal engines can generate higher thrust efficiency and enable faster transit times. They utilise nuclear reactions to heat a propellant like hydrogen, which then expands and expels at high velocity to propel the spacecraft. Reducing journey time from 9 months to just over 6 could improve crew safety, cut radiation exposure, and optimise logistics. Though still in development, this innovation promises to make missions shorter, safer, and more sustainable. Next are life support and habitat technologies, the backbone of human sustainability on Mars. Since returning isn't part of the current plan, focus is on making life on Mars viable long-term or permanently. Closed-loop systems, inspired by International Space Station technology but more advanced, are being developed to recycle air, water, and waste. These systems aim to create a self-sustaining environment so astronauts can survive and work without constant resupply missions. Habitat construction innovations also open new horizons. Traditional spacecraft habitats are bulky and limited. Researchers are exploring in-situ resource utilization, ESRU, to turn Martian soil and ice into building materials and fuel. 3D printing with local materials could soon allow astronauts to erect habitats, workshops, and landing pads directly on the surface, reducing the need to carry everything from Earth. This approach, often called living off the land, could cut mission costs and increase habitat safety and comfort. Energy supply on Mars presents another challenge. Solar power has been common but is hampered by dust storms and the planet's distance from the Sun. To address this, nuclear power sources are gaining attention. Small, compact reactors like NASA's Kilo Power project aim to provide consistent, reliable energy, enabling operations during dust storms and winter months. These reactors offer a scalable, safe, and long-lasting energy source, ensuring critical systems and habitats remain operational regardless of external conditions. Communication technology is evolving rapidly. As humans go further into space, maintaining real-time, reliable contact with Earth becomes more complex. Standard radio signals take up to 20 minutes to traverse Mars-Earth distance, complicating operations in emergencies. Advanced deep space communication networks, including laser-based optical systems, are being developed. These can deliver data hundreds of times faster than current radio systems. Such innovations allow astronauts to stay better connected, receive real-time updates, and transmit high-resolution scientific data with less delay, crucial in the harsh environment of Mars. Navigation and autonomy tech are equally essential. The vast distance limits manual control and decision-making for many tasks. Autonomous robots and drones with AI algorithms are being designed for independent construction, exploration, and repairs. This reduces labour and risk for human crews, freeing them for scientific work. Advanced rovers and aerial drones can map terrain, scout resources, and help build infrastructure, broadening exploration capabilities. Artificial intelligence and machine learning are central to this ecosystem. These technologies analyse vast data, predict system failures, optimise resource use, and adapt to environmental changes. AI-driven life support systems can modulate oxygen, temperature, and humidity to sustain health and comfort. AI-controlled robots can perform mining, drilling, and repairs that would otherwise require human presence. This integration extends operational efficiency and safety. Advances in medicine and health monitoring also support long isolated missions. Miniaturized diagnostics, telemedicine, and genetic analysis kits enable remote and efficient medical interventions. Developing pharmaceuticals optimized for space preserves astronaut health during journeys potentially lasting over a year. These innovations are vital as human presence on Mars could involve prolonged stays with limited external medical support. All these technologies form an interconnected ecosystem that makes reaching Mars feasible. Collaboration among NASA, international agencies, and private firms like SpaceX and Blue Origin accelerates innovation. Each breakthrough feeds into the next, closing the gap between possibility and reality. The synergy of propulsion, sustainable life support, in-situ resource utilization, nuclear power, high-speed communications, autonomous systems, AI, and medical advances transforms Mars from a distant, inhospitable planet into an accessible destination. They turn conceptual ideas into ongoing projects, bringing us closer to stepping onto Mars and potentially staying there, with return plans not necessarily part of the strategy. As we stand on the edge of this new chapter, it is clear these innovations define the future of space travel. They embody our relentless pursuit of discovery, ingenuity, and resilience. Going to Mars isn't just exploration, it's expanding human horizons. With these technological advancements, we are finally equipped to make that leap. The journey to Mars has always been a race against time, challenging humanity's ingenuity and technological limits. The first robotic probes relied on basic rocketry principles, staged solid and liquid fuel engines to push beyond Earth's atmosphere. These systems were reliable but slow, turning what should have been months-long trips into voyages lasting 9 months or more, depending on planetary alignment. As ambitions for human exploration grew, the need to cut travel time became urgent. Faster trips meant less radiation exposure, fewer health risks, and reduced psychological strain for astronauts. Over decades, propulsion technology evolved significantly, driven by scientific curiosity and the goal of making Mars missions feasible and sustainable. Early improvements focused on optimizing existing chemical propulsion. Engineers refined propellant combinations, such as cryogenic liquids like liquid hydrogen and oxygen, and developed more efficient engine designs like staged combustion cycles. These advancements increased specific impulse, improving performance and reducing transit times. Nonetheless, chemical thrusters faced inherent energy density limitations, capping how fast crewed or heavy payload missions could go. Seeking to overcome these limits, scientists explored alternative propulsion methods capable of propelling spacecraft faster and more efficiently. Electric propulsion, particularly ion and Hall effect thrusters, used electric fields to accelerate tiny ionized particles, generating a gentle but continuous thrust over extremely long periods. While offering high specific impulse, these systems produced low thrust, making them suitable for station keeping and in-space maneuvers, but less effective for rapid transits. Discussions and experiments also focused on nuclear thermal propulsion, which has quietly evolved over decades. These engines use a nuclear reactor to heat a propellant like hydrogen, producing thrust with about twice the efficiency of chemical rockets. This technology could cut travel times from 9 months to 3 or 4 months, significantly reducing risks associated with prolonged space exposure and enabling faster missions. More revolutionary progress is seen in concepts rooted in advanced physics, such as plasma drives, solar sails, and fusion engines. Photonic propulsion uses intense laser beams to propel sail-like spacecraft at near-light speeds. Although still experimental and limited to small payloads, these systems could potentially shrink travel times to weeks. A laser-powered solar sail could continuously accelerate a spacecraft across the solar system, vastly reducing interplanetary transit times. Fusion propulsion, often called the holy grail of space travel, harnesses the power of nuclear fusion, the same process that fuels the sun, to generate enormous energy. Fusion engines would produce high-velocity plasma exhaust, enabling faster, more efficient travel. Laboratory experiments like tokamaks and inertial confinement devices aim to control fusion reactions. If successful, fusion engines could halve current transit times, making trips from 9 months down to perhaps 3 or 4 months, opening new horizons for crewed missions. Antimatter propulsion offers the potential for even more dramatic advances. Matter-antimatter annihilation releases tremendous energy, vastly surpassing chemical or nuclear reactions. Controlled antimatter engines could push spacecraft to relativistic speeds, shrinking trips to weeks. However, current challenges include production, containment, safety, and energy management, but ongoing advances in particle physics give hope that antimatter propulsion might become viable in the future, transforming interplanetary travel into nearly instantaneous journeys. Faster propulsion directly benefits human exploration. The longer astronauts are exposed to space radiation and microgravity, the greater the health risks. Solar and cosmic rays cause cancer, degenerative diseases, and other health problems. Accelerating trips significantly reduces these dangers by shrinking mission durations, making human settlement more practical and safer. Safety, reliability, and efficiency remain key concerns. For example, nuclear thermal technology offers a favourable balance, with higher thrust and efficiency based on well-understood principles and manageable regulatory hurdles. In contrast, fusion and antimatter systems, while promising, are still largely experimental, requiring years of research, testing, and international cooperation before deployment. They also bring unique risks and technical hurdles needing addressing. The evolution of propulsion is complemented by advancements in spacecraft design, materials science, and life support systems. Improvements in radiation shielding, habitat design, and autonomous systems are vital to ensuring crew health and mission success, especially on accelerated journeys. These innovations work in tandem, ensuring that when faster propulsion becomes feasible, the entire system, from launch to landing, can operate safely and efficiently. Political and economic factors also influence propulsion development. Governments, space agencies, private companies, and international coalitions now invest heavily in propulsion research, driven by scientific interest and strategic commercial goals. SpaceX's Starship, for example, aims for rapid, fully reusable rockets capable of bringing humans to Mars within a few months. NASA's ongoing nuclear thermal research seeks to unlock more efficient transit systems, supporting exploration and colonization goals. Each propulsion breakthrough reduces the cost, risk, and duration of interplanetary travel, turning distant worlds into more accessible destinations. As science and engineering progress, the vision of reaching Mars shifts from distant hope to achievable reality. Longer term, faster travel could enable not just exploration but human colonies, shifting from visits to permanent settlements. Propulsion advances are part of a broader transformation in space exploration. As technology matures, missions become more efficient, safer, and capable of deeper space travel. These innovations not only facilitate faster trips to Mars, but also pave the way for crewed missions to asteroids, lunar bases, and beyond. The synergy among propulsion, spacecraft systems, and supporting infrastructure will enable a new era of space exploration. In conclusion, the evolution of propulsion technology reflects humanity's relentless pursuit to explore and expand into space. From chemical engines to nuclear, electric, and theoretical constructs like fusion and antimatter drives, each step brings us closer to making interplanetary travel faster, safer, and more sustainable. These advancements are vital for realizing the dream of a human presence on Mars and ultimately exploring the cosmos, transforming science fiction into science reality. Surviving and thriving on Mars depends on revolutionary life support and habitat technologies that transform the red planet from a hostile wasteland into a livable environment. It's not enough to bring supplies and hope. Creating a self-sufficient ecosystem capable of withstanding extremes, daytime temperatures over 250 degrees, nighttime drops below 100 degrees, pervasive radiation, and a thin carbon dioxide-rich atmosphere is essential. Engineers and scientists develop advanced systems inspired by Earth analogues like Antarctic stations and underwater labs, but Mars demands capabilities beyond current technology, emphasizing reliability, efficiency, and autonomy. Life support systems enable humans to breathe, hydrate, and stay healthy. The Martian atmosphere isn't breathable, with atmospheric pressure about 1% of Earth's filled with dangerous CO2. Carbon dioxide scrubbers are critical, utilising lithium hydroxide filters or regenerative amine-based scrubbers heated to release CO2 for reuse. These systems must be powered reliably and maintained regularly, making durability paramount. Oxygen production on Mars relies heavily on in situ resource utilisation, ESRU. Extracting oxygen directly from the atmosphere is key. Processes like atmospheric electrolysis or MOXIE, Mars Oxygen In Situ Resource Utilisation Experiment, heat Mars air, separating oxygen molecules to provide a renewable supply. Larger-scale electrolysis of water from subsurface ice deposits, abundant in some regions, can supplement oxygen needs, creating a sustainable cycle. Water management is another cornerstone. Water is scarce, and extracting it is a focus of ongoing research. Technologies like microwave or thermal extraction heat ice in soil or deposits, releasing vapour that can be captured and purified. Once collected, water circulates through life support systems for drinking, cooking, hygiene, and oxygen generation. Recycling and purification are critical, with systems including dual-stage filters, UV sterilisation, and chemical treatments ensuring water safety over extended periods. NASA's water recovery system, used on the International Space Station, serves as a prototype, but Mars requires more autonomous solutions. Temperature and atmospheric pressure must be stabilised within habitat modules, which face wild environmental fluctuations. Insulation, heating systems, and pressure regulators maintain Earth-like conditions. Electric heaters powered by nuclear or solar sources are typical, while habitat materials, layered composites, regolith-based shielding, help protect from temperature swings and radiation. Some designs involve underground habitats where terrain provides natural radiation shielding, creating a safe, controlled environment. Habitat design also involves integrating local resources. Inflatable or deployable habitats can be assembled on site, lightweight during transit and expandable once on Mars. Multi-layered materials reflect heat, insulate from cold, and provide radiation shielding. Some habitats incorporate regolith-based structures or are built underground, leveraging terrain for natural protection. Ensuring longevity and resilience is critical, especially against dust storms, weeks-long events that can obscure entire sites and damage equipment. Systems must be dust-resistant with robust airlocks and repair protocols. Life support systems include redundancy and autonomy, capable of functioning with delayed or interrupted communication with Earth. Power generation underpins all life support systems. Solar panels are straightforward but less effective during frequent dust storms. Nuclear options like radioisotope thermoelectric generators, RTGs, or small modular reactors offer continuous, reliable energy. A combination of solar and nuclear power ensures energy security for oxygen production, water processing, habitat maintenance, and scientific activities. Atmospheric control and waste management also play vital roles. Cultivating sustainable food sources involves closed-loop bioregenerative systems, integrating hydroponics, aeroponics, and microbial life to recycle nutrients, produce oxygen, and provide fresh food. Recycling organic waste and deploying waste-to-resource technologies reduce reliance on Earth resupply missions, fostering independence. Radiation shielding is crucial, given Mars' lack of a magnetic field and thick atmosphere. Thick layers of regolith or advanced materials like hydrogen-rich polymers can diminish radiation exposure. Building habitats within lava tubes, natural volcanic tunnels, offers natural protective environments, reducing surface radiation risks. Advancing these interconnected systems, air and water recycling, oxygen generation, temperature regulation, radiation protection, and food production, is fundamental for safe, long-term human presence on Mars. Each component must operate reliably over many years, often without maintenance, in unpredictable conditions. Establishing a permanent Mars colony involves more than launching payloads and erecting structures. It requires developing resilient, autonomous, and regenerative technologies. These systems would convert the barren, icy landscape into a new frontier of human exploration. Each innovation brings us closer to calling Mars home, even if initial plans involve limited returns. For many settlers, returning to Earth might remain impossible, emphasizing sacrifice, ingenuity, and adaptability. Living on Mars demands revolutionary life support and habitat systems capable of withstanding extreme conditions, protecting humans from radiation, conserving water, producing oxygen, and maintaining stable environments. The challenge is to create an ecosystem of resilient, sustainable technologies that can operate independently and endure the harsh environment for years. Efforts continue to improve systems like air and water recycling, renewable oxygen production, thermal control, and radiation shielding. Integrating these elements into a cohesive, autonomous infrastructure is essential for survival and self-sufficiency. This not only ensures the safety and well-being of inhabitants, but also reduces dependence on Earth resupply missions, making a long-term presence feasible. As Mars colonization progresses, innovations in habitat construction, such as inflatable modules, subterranean structures, and regolith-based shields, will be vital. Developing systems for sustainable food production via hydroponic farms and microbial support will enable settlers to grow their own food, further fostering independence. Dust storms and environmental hazards will challenge resilience, but robust design and autonomous maintenance will be key to overcoming these obstacles. Power systems combining solar with nuclear options will provide continuous energy, essential for all operations from life support to scientific experiments. Waste management and resource recycling will create closed loops that maximize sustainability, reducing the need for resupply missions. Building habitats with natural and engineered shields will mitigate radiation risks, enabling long-term human occupation. The integration of these critical systems, air and water recycling, oxygen extraction, temperature and radiation control, food production, is essential for transforming Mars from an uninhabitable terrain into a sustainable human environment. Each system must operate seamlessly, reliably, and autonomously, often without immediate human intervention. The path to a functional Martian colony hinges on these technological advancements, pushing the boundaries of current capabilities. Developing resilient, self-sustaining habitats and life support systems will determine whether humans can thrive on Mars. Progress in these areas leads us closer to turning the dream of long-term colonization into reality, shaping a new chapter of human exploration and resilience. The effort is not just about survival, it's about establishing a foundation for human civilization on another planet. This requires overcoming unique challenges and innovating continuously. In doing so, humanity extends its reach beyond Earth, embracing new frontiers with ingenuity, adaptability, and vision. The future of living on Mars depends on mastering these technologies, driven by the resolve to survive, explore, and eventually thrive in space. Artificial intelligence, AI, and robotics are crucial to humanity's efforts to explore, understand, and colonize Mars, turning ambitious visions into reality. They serve as explorers, engineers, scientists, and our eyes on a planet over 140 million miles away. These technologies have transformed Martian research and operations, enabling missions that would be far riskier or impossible without them. Beyond reconnaissance and scientific discovery, AI and robotics are central to creating a sustainable human presence, ensuring safety, efficiency, and long-term success in interplanetary expansion. In early Mars exploration, robotics are indispensable for reconnaissance. The hostile environment, marked by unpredictable weather, dust storms, extreme temperatures, and rugged terrain, limits human activity. Robots act as primary explorers, with rovers like NASA's Perseverance demonstrating autonomous navigation in complex terrain, collecting soil and rock samples, capturing high-resolution images, and identifying hazards with minimal human input. They gather critical data, informing mission strategies, selecting scientific targets, and mapping safe pathways. Deploying autonomous robots reduces risks to humans, conserves resources, and accelerates discoveries. AI enhances robotic capabilities by providing autonomy, decision-making, and learning abilities. Unlike early missions relying on constant ground control, modern AI-equipped robots analyze surroundings, recognize geological features, and adjust operations independently. Due to a communication delay of up to 20 minutes one way between Earth and Mars, real-time control is impossible. AI allows robots to navigate uncharted terrain, select promising sites, and avoid hazards autonomously. For instance, AI can evaluate soil composition, decide whether to drill or collect samples, and reroute around obstacles, speeding exploration. AI also bolsters operations during challenging environmental conditions. Dust storms, obscuring solar panels, reducing visibility, and disrupting communications persistently threaten Mars missions. AI-powered systems manage power distribution, adapt schedules, and protect equipment internally, ensuring scientific experiments and habitat systems function despite these challenges. During low-light periods, AI optimizes energy use, manages batteries, and sustains critical systems, increasing resilience and robot longevity. Robotics driven by AI are vital in constructing habitats and infrastructure for human colonization. Autonomous robots can assemble modules, dig tunnels, lay power and communication lines, and build protective barriers. These complex, physically demanding tasks are initially difficult for humans, especially given the hostile environment, extreme temperatures, radiation, and limited mobility. AI-guided robots perform these activities efficiently, often in environments inaccessible or dangerous for humans. Rapid, reliable infrastructure assembly shortens and reduces costs for establishing sustainable bases. Resource utilization, often called ESRU, in situ resource utilization, is another key application. AI-guided robots identify, extract, and process resources like water ice, minerals, and atmospheric gases. Extracted water can be purified for drinking, converted into fuel, or used for agriculture. CO2 from the atmosphere can be turned into oxygen and hydrocarbon fuel. These processes are essential because transporting supplies from Earth is costly and limited. AI algorithms enable autonomous adaptation of extraction techniques based on environmental data, optimizing resource recovery over time. This transforms Mars from a barren terrain to one that can support human life with minimal external resupply. Scientific discovery advances exponentially via AI-powered systems. Robots can operate as self-sufficient laboratories, performing experiments and interpreting data in real time. Advanced image recognition and pattern analysis help identify signs of past microbial life, habitable zones, or phenomena unnoticed by humans. Self-learning AI can refine hypotheses, adjust investigations, and suggest new research directions, accelerating breakthroughs and deepening understanding of Mars's geology and history. This efficient use of limited mission resources enhances scientific return. Designing robust AI architecture is essential for success in the unpredictable Martian environment. Redundant hardware and software systems manage failures and maintain operations. If a robot malfunctions, AI can reroute tasks, initiate repairs, or adapt plans to minimize downtime and avoid costly human intervention. These systems are built to withstand radiation, dust, and environmental stresses, using machine learning to improve resilience over time. Long-term operations require such adaptability, especially where maintenance and repairs are limited and costly. Safety considerations are paramount. AI and robotics improve safety by enabling robots to explore hazardous zones, to assess environments or collect samples without risking human lives. AI monitors robotic health, predicting failures, and scheduling preventive maintenance remotely. In emergencies, AI can execute protocols, such as sealing breaches or shutting down systems, protecting human missions and infrastructure. These capabilities create a safer, more resilient environment for future human exploration and colonization. AI and robotics also reshape planetary exploration itself. They extend human curiosity, enabling investigation of environments at depths and scales previously impossible. These technologies test new systems, develop sustainable living modules, and probe Mars's hidden secrets, like subsurface lakes, mineral deposits, and biosignatures. They serve as testing grounds for innovations necessary for future projects, including interstellar probes or orbital habitats, with lessons enhancing subsequent missions. As AI technology progresses, systems become increasingly autonomous, capable of learning and adapting from experience. This reduces dependence on Earth-based control, allowing robots to operate independently over long periods. Humans set strategic objectives, interpret data, and guide long-term planning, while AI handles operational duties, repetitive tasks, and environmental uncertainties. This partnership greatly expands exploration potential, making colonization, research, and resource development more feasible. However, reliance on autonomous AI raises ethical, control, and reliability concerns. Transparency in AI decision processes, safeguards against unintended actions, and fail-safe systems are critical. Ethical issues include AI's potential to make moral judgments or adapt in ways conflicting with human values. Addressing these challenges involves collaboration among engineers, ethicists, and policymakers to create guidelines for deploying AI in space missions, ensuring safe, responsible use. The benefits of integrating AI and robotics extend to Earth industries, space robotics innovations, advanced sensors, machine learning algorithms, autonomous controls, find applications in medicine, manufacturing, disaster response, and environmental monitoring. The push to explore Mars drives technological advances that benefit society at large, inspiring new generations of scientists, engineers, and innovators. These advancements foster societal progress through technological spin-offs and new industries. Ultimately, AI and robotics are indispensable partners on the journey to Mars. They bear physical and cognitive burdens, navigate hazardous terrains, and unlock secrets beneath the surface. Their capabilities amplify human effort, accelerate scientific discovery, and build the foundation for a sustainable presence. Without them, reaching, exploring, and inhabiting Mars would remain impossible. With their aid, that dream is increasingly tangible, bringing us closer to understanding our place in the universe, fundamental questions of life's origins, and perhaps establishing a second home for humanity. The synergy between humans and intelligent machines shapes the future of space exploration, unlocking possibilities beyond our imagination and ushering in a new era of discovery and adventure. The journey to Mars involves more than just spacecraft and habitats. It's a race against the profound effects prolonged space travel can have on the human body. Leaving Earth's gravity behind, the human body faces new challenges, many only partly understood. The risks are significant, and understanding them is crucial for astronaut health and safety. One immediate issue in space is bone loss. On Earth, gravity stimulates bones to stay dense and strong. In microgravity, this stimulation is absent and bones weaken rapidly. ISS studies show astronauts can lose up to 1% of their bone density monthly. Weakened bones increase the risk of injuries or fractures during and after missions. Scientists are exploring drugs and specialized exercises to mimic gravity and preserve bone strength during extended spaceflight. Muscle atrophy is another concern. Without gravity's resistance, muscles supporting movement, especially in the legs, back, and abdomen, shrink and weaken. After only a few weeks in space, astronauts notice reduced muscle mass and strength. Longer missions worsen these effects, impairing performance on Mars and upon returning to Earth. Resistance training helps mitigate muscle loss, but without recreating Earth's gravity, eliminating atrophy entirely is impossible. Cardiovascular health also declines during long missions. Earth's gravity aids blood circulation, helping blood return from lower extremities to the heart. In space, blood pools in the upper body and head, causing issues like spaceflight-associated neuroocular syndrome, leading to vision problems. Microgravity can weaken the heart's efficiency. Fluid shifts and decreased plasma volume cause orthostatic intolerance, difficulty standing without dizziness, upon return to Earth or other gravity environments. Extended space travel impacts the immune system too. Astronauts often show weakened immune responses, increasing susceptibility to infections and slowing recovery. The space environment lacks exposure to microbes that bolster immunity, while stress, confinement, altered sleep, and radiation worsen vulnerability. A compromised immune system poses risks, especially when encountering unfamiliar microbes on Mars. Radiation exposure is perhaps the greatest threat. Unlike Earth's atmosphere and magnetic field shielding against harmful radiation, spacecraft and habitats on Mars are exposed to cosmic rays and solar energetic particles. Over time, these rays damage DNA and cells, increasing cancer risk. Studies suggest astronauts on Mars might face double or triple their lifetime risk of cancer. Radiation may also cause degenerative diseases, cardiovascular issues, and neurological effects like cognitive decline. Cognitive effects are concerning as well. Microgravity and radiation influence brain function, leading to sensory and perceptual changes. Long-term radiation may cause memory loss, reduced decision-making skills, or mood disorders. Psychological stress from confinement, isolation, and limited communication further exacerbates issues. The interconnectedness of mind and body means health relies on mental resilience alongside physical well-being. Sleep disturbances are common in space, especially during long missions. Microgravity affects sleep patterns, and the absence of natural light cycles disrupts circadian rhythms. Poor rest impairs cognition, mood, and immune responses. Chronic sleep deprivation weakens overall health and increases vulnerability to other health risks associated with space travel. These risks demand innovation and foresight. To combat bone loss, efforts include medications and resistance training protocols. For muscle atrophy, advanced exercise devices simulating gravity are under development. Cardiovascular health is managed with monitoring and reconditioning, but challenges persist, especially once astronauts land on Mars, where gravity is only about 38% of Earth's. Addressing radiation involves advanced shielding, drugs, and potential gene editing to repair or protect cells. These health risks highlight the toll space takes on the human body, with the thin line between routine missions and life-threatening emergencies. As we strive for sustainable Mars presence, understanding these risks remains vital. They form the foundation for safety protocols, drive technological innovation, and reflect human resilience. Lessons learned from these challenges bring us closer to safer, longer journeys beyond Earth's orbit. Every step forward turns challenges into opportunities, paving the way for interplanetary exploration. Addressing these risks is essential for future missions. NASA and other agencies are developing new technologies, protocols, and treatments to mitigate health issues. Pharmaceuticals and enhanced exercise routines target bone and muscle loss. Devices simulating gravity are being tested to lessen atrophy. Monitoring systems help maintain cardiovascular health, though challenges remain once on Mars. Shielding materials and pharmacological countermeasures are developed to reduce radiation exposure, with gene editing possibly offering future solutions. Overall, space health management involves a multifaceted approach, combining technology, medicine, and psychological support. Preventive measures and prompt responses are crucial for managing risks. Recognizing early signs of health issues and maintaining communication with ground teams help ensure safety. The psychological aspect is equally important. Providing mental health support and fostering resilience are vital components of mission planning. Long-duration spaceflight pushes human limits, but each challenge offers an opportunity for discovery and innovation. Advancements in medical technology, engineering, and understanding physiology will be key to safeguarding astronauts. The goal is to develop effective countermeasures that allow humans to thrive during long journeys and settlements beyond Earth. Threats posed by microgravity, radiation, and behavioral stresses underscore the need for comprehensive health strategies. Continuous research, real-time monitoring, and adaptive protocols will improve outcomes. As we prepare for the future, these insights will inform spacecraft and habitat design, creating safer environments for interplanetary exploration. In conclusion, long space missions carry significant physical health risks including bone loss, muscle atrophy, cardiovascular deconditioning, immune suppression, radiation damage, cognitive impairment, and sleep disturbances. Addressing these challenges requires coordinated efforts across disciplines, technological innovation, and a deep understanding of human physiology. Only through persistent research and adaptive strategies can we ensure explorer safety and health. The lessons learned today will shape the future of human space exploration, enabling us to venture beyond our planet with resilience and confidence. Radiation exposure is one of the most significant dangers facing humans venturing to Mars, posing risks that could alter health or end missions early. Unlike Earth, protected by a thick atmosphere and magnetic field, Mars is barren and exposed. Its thin atmosphere offers minimal defense against solar and cosmic radiation, leaving the surface vulnerable to relentless high-energy particles. On the journey to Mars, astronauts encounter radiation hazards from departure. Galactic cosmic rays, charged particles from beyond our solar system, travel near light speed, penetrating spacecraft hulls and tissues. Unlike Earth's predictable environment, these rays are unpredictable and cause complex cumulative damage over time. Once on Mars, dangers persist. The planet's sparse atmosphere doesn't offer significant shielding. Surface radiation levels are markedly higher than on Earth, posing health risks. Continuous exposure raises concerns about short-term and long-term effects on astronauts' health. A primary threat is DNA damage. High-energy particles cause ionization, breaking DNA strands and inducing mutations. Short-term, radiation causes cell death, impairing cellular functions, resulting in nausea, fatigue, or acute radiation sickness at high doses. Long-term, DNA mutations can lead to cancers such as leukemia, brain tumors, or other malignancies, especially with prolonged exposure. making cumulative doses a serious concern for extended missions or habitats. Radiation also impacts the nervous system. High-energy particles penetrate neural tissues, causing cellular and molecular damage. Studies show that elevated radiation can impair cognition, memory, and cause mood changes. These neurological effects threaten decision-making, mission success, and crew well-being. Cardiovascular health is another concern. Emerging research suggests high doses may accelerate atherosclerosis, increasing heart attack and stroke risks. Space conditions, reduced physical activity, radiation, and stresses combine to jeopardize cardiovascular health over time. Beyond biological effects, radiation damages equipment and electronics vital for life support, communication, and navigation. High-energy particles can cause malfunctions or destruction of sensitive components, risking life-threatening situations if backup systems or shielding are inadequate. Protecting hardware increases spacecraft weight and complexity, raising costs and design challenges. Protective strategies are under study. Shielding materials, like dense polyethylene or water, absorb radiation before reaching humans. However, shielding adds weight, complicating launches and landings. Researchers explore harnessing the Martian environment itself, using regolith, loose soil and dust, to construct underground habitats or berms around surface structures, offering substantial protection. Developing underground bases or lava tubes, natural volcanic tunnels, could provide shelter from solar and cosmic radiation with minimal additional shielding. Biological countermeasures are also under investigation. Antioxidants and radioprotective agents may reduce cellular damage caused by radiation. Substances like melatonin or amino acids could mitigate oxidative stress. Future research explores gene editing and biotechnologies to enhance human resilience against radiation damage, though these methods remain experimental. Pre-mission planning involves assessing radiation doses astronauts will receive. Dosimeters on spacecraft and crew measure real-time levels, guiding safety protocols. Missions aim to launch during periods of minimal solar activity, when cosmic rays are less intense, and to limit cumulative doses through strategic mission durations and timing. Understanding individual susceptibility is vital. Not all humans respond equally to radiation. Genetic factors influence resilience. Personalized medicine, like pre-mission genetic screening, can help select crew members with higher resistance, reducing health risks. Despite these strategies, full protection remains elusive. No current methods eliminate all risks. Many experts accept some health hazard is inherent in Mars missions. The decision to proceed involves weighing scientific and pioneering benefits against potential health dangers of radiation. This underscores the importance of ongoing research, technological advances, and safety protocols. Improved shielding, habitat design, and medical countermeasures are steps forward. Each innovation brings humanity closer to safe Mars exploration and settlement. Still, radiation remains a formidable obstacle, reminding us that the journey is as much about mastering these challenges as exploring the planet itself. The understanding of radiation hazards influences mission planning profoundly. It affects habitat design, mission duration, timing, and health monitoring. Every decision is driven by the relentless nature of high-energy particles. Accepting some risk may be necessary for human expansion into space. As we advance, we acknowledge that traveling to Mars is a test of resilience. The journey involves confronting the universe's most powerful forces, with some risks unavoidable. Many believe this voyage may be ultimately one way due to the dangers posed by radiation and other hazards. Sustaining health and life for a return trip is nearly impossible under current conditions. The risks impose a sacrifice rooted in curiosity, resilience, and the human spirit's drive to explore, despite the universe's harshness. Radiation's threat emphasizes the urgency of innovation in protection. Developing lightweight shielding, underground habitats, pharmacological aids, and genetic enhancements are critical. These efforts aim to mitigate risks, making long-term human presence on Mars feasible. With continuous progress, humanity edges closer to overcoming radiation's barrier, turning what once seemed insurmountable into manageable risks. Ultimately, understanding and addressing radiation hazards are central to mission planning and safety. From habitat design to medical protocols, every aspect hinges on managing high-energy particles. They are relentless, and accepting some level of risk might be necessary for progress. The journey to Mars is as much about mastering these dangers as it is about exploration itself. The unyielding nature of radiation compels us to accept that some hazards will always exist. As technological solutions evolve, so too will our capacity to protect astronauts. Still, the inherent risks highlight the importance of cautious advancement and innovation driven by scientific understanding. Proceeding with awareness, preparation, and resilience will be vital for humanity's successful leap to the red planet and beyond. Living and working on Mars presents extraordinary psychological challenges, unlike anything most people have experienced. Being hundreds of millions of miles from Earth, cut off from familiar sights, sounds, and comforts, creates immense strain. Confined inside a habitat no larger than a suburban house, crew members are surrounded by the barren, hostile landscape of the red planet. The closest human contact may be hours or days away, and communication with Earth can take minutes or hours. Such conditions impose significant psychological stress, making it crucial to understand these challenges for the success and well-being of future Martian explorers. Loneliness is the first major hurdle. Unlike astronauts aboard the International Space Station with nearby colleagues, Mars crews face months or years of isolation from the outside world. Being cut off from friends, family, and Earth can be overwhelming. This isn't just about missing loved ones. It's about profound loneliness from the absence of human contact in a close-knit environment. Even with video calls or messages, the knowledge that Earth is days away fosters a persistent feeling of disconnection. Over time, this loneliness can lead to depression, anxiety, and emotional exhaustion, especially during stressful periods or emergencies. Boredom and monotony are also significant psychological challenges. Daily routines on Mars will likely be repetitive, involving scientific experiments, maintenance, exercise, and communication with Earth. With limited recreational options, crew members may experience mental fatigue from sameness. The absence of spontaneous social interactions, diverse environments, or new experiences that keep minds engaged on Earth can make time drag and diminish mental resilience. Such monotony erodes morale and can impair decision-making skills. Conflicts among crew members pose another serious challenge. Living in tight quarters with constant proximity and the high stakes of their tasks increases the risk of disagreements. Small irritations can escalate when space is limited and stress is high. Unresolved conflicts threaten mental health and mission success. Maintaining a healthy team dynamic becomes essential, requiring emotional intelligence, empathy, and resilience, alongside professional competence. The inherent risks and dangers of the mission also weigh heavily. Crew members remain acutely aware that mistakes or accidents could be catastrophic, with no rapid rescue option. This ongoing perception of danger can generate constant anxiety, which may intensify during emergencies or equipment failures. Living under such threat continuously can lead to chronic stress, sleep disturbances, or post-traumatic stress if crises occur. The psychological toll of living in a hazardous environment cannot be underestimated. Sleep disruption and circadian rhythm disturbances are common in isolated environments, even in space. Without natural Earth patterns and with artificial lighting, astronauts often struggle with maintaining consistent sleep. On Mars, carefully designed lighting and scheduling are vital to promote rest. Poor sleep exacerbates other psychological issues, impairs decision-making, and reduces emotional stability, creating a cycle that endangers crew health and mission effectiveness. The unpredictability of life on Mars adds further stress. The environment is unforgiving, dust storms lasting days, extreme weather, and the knowledge that rescue is unavailable whenever needed. This persistent threat heightens the feeling of living on the edge. The environment itself becomes a psychological burden, forcing crew members to confront fears repeatedly. Adapting to an alien landscape and artificial habitats requires mental flexibility and resilience. Human beings are innately accustomed to Earth's gravity, atmosphere, and natural surroundings. Adjusting to lower gravity, stark landscapes, and unfamiliar habitats demands psychological adaptation. The crew's culture must foster purpose, shared identity, and optimism to counter feelings of dislocation or alienation. This adaptability is crucial for mental health and mission cohesion. The importance of mental health support cannot be overstated. While physical health management is well understood, psychological well-being requires proactive strategies. On Earth, mental health services are easily accessible, but on Mars, support will likely be remote. Through teletherapy, AI mental health tools, or other means, Regular check-ins, stress management activities, and opportunities for recreation help sustain morale. Creating routines that include hobbies, social interactions, and moments of levity is vital for psychological resilience. Social dynamics within the crew are critical. Trust, empathy, and effective communication form the foundation of a successful mission in such an isolating environment. Crew members need skills to handle conflicts and manage their emotional responses. Building a resilient community that supports each other emotionally helps prevent psychological disruptions that could threaten safety or mission objectives. Promoting a culture of openness and mutual support is essential. Individual differences significantly influence coping mechanisms. Some crew members may find solace in routines, hobbies, or spiritual practices, while others might struggle with despair or helplessness. Recognizing and accommodating these differences through tailored support programs and resilience training is necessary. Psychological screenings before deployment and ongoing mental health monitoring can help identify those at risk and ensure they receive appropriate support. A strong sense of purpose is a vital psychological anchor. Knowing their work advances humanity's greatest exploration can motivate crew members intensely. Cultivating shared goals, reinforcing the mission's significance, and celebrating small successes bolster mental resilience. Fostering hope and maintaining a connection to Earth and each other serve as vital anchors amid the psychological turbulence of such an extraordinary journey. The psychological challenges of Mars are as demanding as the technical hurdles. Addressing them requires a comprehensive approach, integrating mental health protocols, team building, environmental design, and ongoing support. Only by actively managing these human factors can we ensure that those venturing to the Red Planet do so with the mental resilience necessary to withstand the journey's emotional and psychological weight. The unpredictable nature of Mars missions creates a ripple of challenges beyond technical hurdles. Every decision must account for unknowns and setbacks that could turn a smooth operation into a crisis. This inherent uncertainty complicates logistics and fundamentally changes how teams think about risk, resilience, and human commitment in interplanetary exploration. One immediate impact of uncertainty is the need for meticulous, flexible planning. Mission designers must anticipate numerous possible scenarios, many seeming improbable at first. Equipment failures, such as malfunctioning life support, navigation instruments, or communication relays, pose significant concerns. Unlike Earth-based projects where troubleshooting can be immediate, fixing issues remotely on Mars involves delays and limited options. Components must incorporate redundancies, fail-safes, and modularity, expanding mission scope and increasing costs. Environmental unpredictability also influences planning. Mars's weather is far less stable than Earth's, with dust storms, temperature swings, and radiation fluctuations. Such variables compel mission planners to develop robust protocols for hardware and human safety. They must prepare for storms that can last days, disrupt visibility, and hinder solar power. Consequently, schedules include delays and contingencies that extend timelines. Habitats and power systems must be versatile enough to withstand these storms, adding further complexity to engineering efforts. Communication delays, ranging from 13 to 23 minutes, pose another major challenge. Real-time decision-making becomes impossible. Mission teams rely on autonomous systems and pre-programmed protocols. This pushes development of advanced AI and robotics capable of interpreting data, making decisions, and executing commands independently. Building such systems isn't straightforward, especially given Mars's unpredictable environment, which demands that they handle unexpected scenarios not explicitly programmed. Autonomous systems introduce additional planning complexities. Engineers need to ensure robots and AI can handle unforeseen problems, unexpected terrain, hardware malfunctions or resource shortages, and adapt in real time. This requires sophisticated algorithms, machine learning, and rigorous testing. The need for high autonomy increases design uncertainty, as developers must anticipate the unpredictable conditions on Mars. Resource availability introduces further uncertainties. Vital resources like water, minerals, and others are limited and unevenly distributed. Technologies are progressing toward in-situ resource utilization, extracting water from soil or converting local minerals, but these methods remain in development. If extraction underperforms or encounters obstacles, habitat sustainability could be threatened. Planning must include backup supplies, flexible resource management, and contingencies for supply from Earth, which is costly and impractical beyond a point. This emphasizes the importance of reliable, adaptable resource extraction. Psychological and operational readiness of crew are also affected by uncertainty. Astronauts face unknowns that could threaten their health, safety, or mental well-being. Mission plans include training for crises, medical emergencies, habitat breaches, equipment failures, communication cutoffs, to prepare crew members to remain calm, resourceful, and adaptable. Despite exhaustive preparation, unpredictable events will test their resilience and problem-solving skills. Mental resilience influences crew selection, training, and habitat design. Teams must be composed of individuals capable of handling stress and ambiguity, working independently, making critical decisions in isolation, and supporting each other. Habitats and life support systems must incorporate redundancy, flexibility, and psychological comfort features, as the outside environment is unpredictable, and social dynamics can be strained by isolation and limited crew sizes. Operational decision-making becomes a delicate balance between caution and progress. Mission leaders weigh risks of proceeding amid uncertainties against potential gains. Decisions may involve postponing activities, rerouting or adjusting plans based on new data. For example, extravehicular activities might be delayed if weather forecasts are uncertain, or terrain obstacles may cause route changes. This requires an adaptable approach that incorporates ongoing information and circumstances, effectively negotiating with uncertainty. Financial impacts are substantial. Uncertainty increases budgets due to the need for redundancies, backup systems, adaptive protocols, and extensive testing. Delays further inflate costs and push timelines, straining funding sources and international partnerships. Sometimes, uncertainties lead to prioritizing safety and reliability over speed, recognizing that rushing increases risks of catastrophe. Uncertainty also prompts shifts in mission goals. Instead of rapid milestones like colonization, missions may focus on incremental progress, building robotic infrastructure, testing resource extraction, gradually expanding capabilities. This cautious, iterative approach acknowledges that a direct path is impractical. Each step aims to build resilience against unforeseen setbacks, emphasizing learning and adaptation. Ultimately, uncertainty shapes the entire architecture of Mars missions. It demands flexible strategies, resilient systems, and autonomy, all while accepting that surprises will always exist. These surprises are part of the exploration narrative, reminding us that pushing frontiers involves risks and unpredictability. Adaptability becomes crucial, as no amount of preparation can eliminate surprises. Instead, our ability to navigate these uncertainties reveals ingenuity, courage, and curiosity. The challenges of Mars exploration underscore human resilience and the importance of embracing the unknown. No matter how well prepared, the Red Planet retains surprises. These uncertainties push us to develop better technologies, foster teamwork, and enhance problem-solving capabilities. They also remind us that exploration is inherently unpredictable, emphasizing humility alongside ambition. In essence, the uncertainty of Mars missions influences planning at every level, from technical design to crew training and operational protocols. It compels us to develop flexible, resilient systems that can handle unexpected conditions. This unpredictability emphasizes the importance of autonomous decision-making, resourcefulness, and mental resilience. It shapes mission goals and budgets, often requiring a cautious, incremental approach. While uncertainty introduces risks and delays, it also fuels innovation and learning. Recognizing and preparing for the unknown is vital for success. It demands adaptive strategies that balance caution with progress, ensuring safety while maintaining mission momentum. The unpredictability of Mars ultimately reflects the nature of exploration itself, an ongoing negotiation with the unknown where human resilience and ingenuity shine. Living and working in microgravity is a fundamentally different experience from Earthbound life. While the view of the Martian surface might be awe-inspiring, the reality for astronauts venturing beyond our home planet is that their bodies undergo profound changes over time in the weightless environment. The effects of microgravity on the human body are extensive, impacting almost every system and posing significant challenges for long-term space habitation, especially when considering a mission to Mars where return might not be part of the plan. One of the earliest and most noticeable effects of microgravity is muscle atrophy. On Earth, gravity pulls us down, requiring muscles, especially those used for posture and movement, to work against this force constantly. In microgravity, the lack of gravitational pull means muscles used for standing, walking, and maintaining posture are seldom engaged. Over days and weeks, this causes a significant decrease in muscle mass and strength. This space-induced muscle wasting affects mainly the anti-gravity muscles of the legs, back, and core. As a result, astronauts' ability to perform physical tasks diminishes, and they often experience weakness and fatigue. Bone density also suffers dramatically in microgravity. Earth's gravity stimulates bone production and maintains mineral density through regular weight-bearing activities. Without this stimulus, bones begin to lose mineral content, leading to space osteoporosis. Within a few months, astronauts can lose as much as 1% of their bone density monthly, especially in load-bearing bones like the hips, spine, and legs. This fragility increases fracture risk and could be debilitating during a Mars mission, where emergency medical resources are limited. The cardiovascular system also undergoes significant changes. In microgravity, fluids shift from the lower extremities toward the upper body and head, causing facial puffiness and nasal congestion that are common during spaceflight. Over time, this redistribution decreases blood volume, a process called hypovolemia, which affects cardiovascular performance, leading to orthostatic intolerance. Astronauts may feel dizzy or faint upon return to Earth's gravity or during gravity transitions on Mars. The heart itself can change shape slightly, becoming less muscular, which can impair pumping efficiency. Microgravity also impacts the sensory and nervous systems. Spatial orientation and balance become disrupted because the inner ear, which relies on gravity to sense motion, receives abnormal cues. Astronauts often report balance and coordination issues that can persist for days or weeks after returning to Earth. Additionally, microgravity affects the central nervous system, leading to sleep disturbances, cognitive changes, and mood alterations. Sleep problems are common and are partly due to constant ambient light and difficulty distinguishing day from night, along with changes in brain chemistry. These factors can cause cognitive decline, attention span reduction, and emotional volatility, emphasizing the importance of mental health and team cohesion during long journeys. The immune system also suffers in microgravity. It impairs immune cell function, lowering the body's ability to fend off infections. Astronauts produce fewer antibodies and immune cells, increasing vulnerability to illnesses. This suppression is exacerbated by space travel stress, confined living conditions, and altered sleep cycles, creating a scenario where infections can become severe and difficult to treat with limited medical supplies available on spacecraft. Gastrointestinal systems are affected too. Microgravity alters the normal functioning of the digestive tract, reducing peristalsis, the muscular contractions that propel food through the system. This can lead to nausea, bloating, and constipation. Furthermore, microgravity influences the microbiome, bacteria in the gut, potentially causing imbalances that impact digestion and overall health. Maintaining a healthy diet and monitoring gut health are critical for long-term missions. Reproductive health in microgravity remains uncertain. Research suggests microgravity may affect sperm motility, egg development, implantation, and pregnancy. The effects on fetal development are unknown, raising ethical and health concerns about reproduction during extended missions. Consequently, colonization efforts might initially rely on non-reproductive strategies, waiting until more is understood and biomedical interventions are advanced. All these physiological changes are interconnected and can compound, making microgravity a challenging environment for human health. The critical challenge for future Mars explorers will be not just survival, but actively mitigating these adverse effects. Countermeasures under development include resistance exercise routines, pharmacological treatments, nutritional support, and artificial gravity solutions. Currently, astronauts exercise about 2 hours daily, using treadmills, resistance devices, and cycling to combat muscle and bone loss. However, these strategies may need significant enhancement or new approaches for missions as distant as Mars, where effects could last months or years. Recognizing microgravity's profound impact on the human body underscores the need for innovative health solutions. As humanity prepares for longer space presence, Mars on the horizon, developing comprehensive countermeasures is essential. Protecting astronaut health isn't solely about returning home safely. It's vital for long-term survival and independence from Earth support, Especially if some explorers won't return, they will become pioneers, living on a distant world and adapting to environments that challenge every biological aspect. This understanding isn't just scientific curiosity, it's the foundation for expanding humanity's presence into the cosmos. Long-term exposure to the space environment presents significant psychological challenges that can alter mental health. When astronauts venture beyond Earth's familiar environment into space's vast, isolating, and often inhospitable realm, they confront both physical dangers and emotional and cognitive stresses that can reshape their mental landscape. As missions extend, such as those planned for Mars, understanding these impacts is crucial for crew safety, mission success, and astronaut well-being. One immediate psychological effect is the sensation of isolation and confinement. Astronauts are confined in small, sealed habitats for months or years, creating a sense of being cut off from the outside world. This fosters loneliness and alienation despite being close to team members. The lack of natural environment, no greenery, sunlight, or open horizon, can lead to emotional disconnection from life outside the spacecraft. The confined environment, with limited personal space and privacy, heightens feelings of being trapped, which can erode mental resilience and lead to depression, anxiety, and irritability. The monotonous space life further compounds stress. Unlike Earth, with its dynamic landscapes and natural stimuli, space habitats are sterile and unchanging. Windows may show starfields or barren planets, but the environment offers minimal variety. This lack of sensory diversity diminishes mood and motivation, contributing to boredom, frustration, or apathy. The absence of natural stimuli impacts emotional health, pushing astronauts toward pessimism or despair. Maintaining enthusiasm and purpose becomes harder, as the environment offers little excitement. A constant source of stress stems from awareness of inherent dangers. Risks such as radiation exposure, equipment failures, and medical emergencies create a persistent state of vigilance and anxiety. Although astronauts are trained to respond swiftly, this hyper-awareness leads to chronic stress and hyper-arousal. Elevated stress levels can impair decision-making and emotional regulation, increasing the risk of mistakes that could jeopardize safety and mission success. Sleep disturbances are another major concern. The disruption of circadian rhythms, caused by artificial lighting, lack of natural day-night cues, and environmental stress, leads to fragmented or insufficient sleep. Sleep is vital for mental health, affecting memory, emotional regulation, and brain restoration. Poor sleep impairs cognition, lowers judgment, heightens irritability, and causes mood swings. It can also amplify fatigue and hopelessness, reducing mental resilience. The deprivation of Earth's natural environment results in a profound sensory deficit. The sights, sounds, and smells that ground humans are replaced by mechanical hums, electronic displays, and the emptiness of space. This sensory deprivation can cause disorientation, hallucinations, or feelings of disconnection from reality. Over time, astronauts may experience space fog, reduced mental clarity and focus. Feelings of alienation deepen, and space becomes more akin to a prison than a frontier of exploration. Chronic stress from space demands adds mental strain. Astronauts monitor habitat systems, navigation, and health metrics constantly, demanding sustained vigilance. This cognitive load can lead to mental fatigue, burnout, and decreased psychological flexibility. The pressure to perform perfectly, coupled with high stakes, heightens anxiety. Over time, mental fatigue hampers performance, emotional regulation, and safety. Routine disruption and altered social dynamics impact mental health profoundly. Earth-based routines, grounded in natural cycles and family ties, are replaced with rigid, artificial schedules designed for safety and efficiency. These routines can feel impersonal or controlling, undermining autonomy and intrinsic motivation. Communication delays, sometimes up to 20 minutes one way, sever emotional bonds and hinder real-time social support. These factors foster loneliness and homesickness, which can lead to despair, depression, or a longing for Earth that feels increasingly unreachable. Space madness, though rare, underscores how space can alter mental states. In extreme cases, such as prolonged confinement, sleep deprivation, or crises, astronauts may experience hallucinations, paranoia, or psychological crises. Such episodes threaten team cohesion and mission integrity, highlighting the importance of psychological resilience and support systems for long missions. Even minor mood or cognition shifts can have outsized impacts when lives depend on mental clarity and teamwork. Scientists and engineers actively explore mitigation strategies. Virtual reality environments mimicking Earth's landscapes aim to provide sensory stimulation and emotional relief. Enhanced psychological support, like confidential communication with Earth-based psychologists, helps astronauts manage stress. Crew training emphasizes resilience, adaptability, and conflict resolution to foster psychological well-being. Routines are being designed to balance structure with autonomy, preserving a sense of control and purpose. Many mental health risks in space remain unpredictable. Long missions to Mars will require ongoing research, tailored interventions, and proactive psychological care. Developing robust mental health monitoring, early distress detection, and personalized support systems is essential to ensure psychological endurance during deep space exploration. Protecting mental health is as vital as safeguarding physical health, because the success of such missions depends on human resilience, the capacity to remain mentally intact amid extreme adversity. In summary, long-term space travel fundamentally alters mental health through isolation, monotony, danger, sleep disturbance, sensory deprivation, routine disruption, and stress. These effects can manifest as depression, anxiety, hallucinations, or psychosis, threatening individual well-being and mission stability. As we explore further into space, understanding, predicting, and mitigating these psychological challenges becomes as critical as technological advancements. The journey to Mars is not just a test of engineering, but a profound test of the human spirit, demanding resilience, adaptability, and an unwavering focus on mental well-being. Only by addressing these psychological needs can astronauts reach their destination and return resilient in mind and body. Radiation's impact on tissue and DNA is complex, with residual effects that challenge long-term human presence on Mars. While immediate effects like acute radiation sickness are more straightforward, the persistent influences on cellular and molecular structures are more insidious and significant, affecting health over years or decades. These lingering effects stem from cosmic radiation encountered during space travel and surface missions, producing biological damage that can accumulate, evolve, and persist, thereby shaping the feasibility of human colonization. Ionizing radiation interacts with tissue mainly by ejecting electrons from atoms, creating free radicals, reactive species that attack cellular components. Lipids in membranes are vulnerable. Lipid peroxidation compromises membrane integrity, increasing permeability, dysfunction, and cell death. Proteins, essential for cellular functions, are also damaged, losing structure and activity due to amino acid alterations or cross-linking. Most critically, DNA absorbs radiation energy, resulting in damage like single-strand and double-strand breaks. Single-strand DNA breaks are generally repairable, involving severing of a single nucleotide chain that cellular mechanisms can fix. Conversely, double-strand breaks are more problematic. They sever both DNA strands and are prone to misrepair, leading to mutations, chromosomal aberrations, or cell death. When repair mechanisms malfunction or are overwhelmed, mutations may become permanent in the genome, underpinning cancer initiation and progression, thus increasing long-term risks for astronauts exposed to sustained radiation. Residual DNA damage can persist long after exposure, especially if repair pathways are defective or overwhelmed. This leads to genomic instability marked by increased mutation rates and chromosomal abnormalities, creating a fertile ground for cancer and genetic disorders. Repeated low-dose exposures, such as ongoing surface radiation or multiple missions, compound damage, gradually eroding genomic integrity. This cumulative effect transforms initial radiation events into chronic threats to cellular health. Damaged mitochondrial DNA, mtDNA, is another significant residual effect. Mitochondria, the energy-generating organelles, have their own genome, which is highly susceptible to reactive oxygen species ROS produced during respiration. Damage to mtDNA impairs oxidative phosphorylation, reducing ATP production and increasing ROS generation, perpetuating a vicious cycle. This oxidative stress damages membranes, proteins, and DNA further, impairing tissue function and promoting aging. Mitochondrial dysfunction is linked to neurodegenerative diseases and metabolic disorders, complicating long-term adaptation to Mars. Beyond direct genetic changes, radiation influences cellular signaling pathways, often inducing premature aging or cellular senescence. Senescent cells cease dividing but secrete inflammatory cytokines, enzymes, and growth factors, a process called SAESP. Accumulation of these cells and chronic inflammation contribute to tissue degeneration, impair wound healing, and foster age-related diseases. This is especially concerning during long Mars missions, where regenerative capacity is vital for recovery. The immune system, especially hematopoietic tissue in bone marrow, is particularly vulnerable. Ionizing radiation reduces white blood cell production, weakening immune defenses and increasing susceptibility to infections. Moreover, immune surveillance against cancerous or abnormal cells is compromised, raising the risk of oncogenic mutations not being adequately eliminated, thus elevating cancer risks over time. Radiation also induces fibrosis, excess connective tissue formation around organs and tissues. While fibrosis can be part of normal wound healing, excessive fibrosis stiffens tissues, impairs elasticity, and reduces organ function. Pulmonary fibrosis could hinder respiration in Mars' thin atmosphere. Similar fibrotic changes in other organs impair functions, exacerbating respiratory and cardiovascular problems, compromising overall health. Long-term consequences include hampered tissue regeneration, since stem cells responsible for renewal are vulnerable to radiation damage. Depleted or mutated stem cells diminish the body's ability to repair tissues, recover from injuries, and maintain organ health. This decreased regenerative potential accelerates aging processes and reduces resilience against environmental challenges encountered on Mars. Systemic effects involve chronic inflammation resulting from accumulated radiation damage, contributing to age-related diseases, from cardiovascular issues to neurodegeneration. The nervous system, especially the brain, is highly susceptible. Microvascular damage impairs blood flow. Neuronal death and oxidative stress contribute to cognitive decline, mood disturbances, and neuropsychological disorders. These effects are worsened by isolation, confinement, and stress inherent in Mars missions, intensifying psychological and neurological vulnerabilities. Research continues into these residual effects, but the biological scars of radiation are undeniable. They leave invisible yet profound marks on tissues and DNA. Mitigating immediate radiation risk is insufficient. Long-term strategies are required. These include developing advanced radioprotective agents, gene editing to repair DNA damage, and regenerative medicine to restore tissue function. Enhancing the body's defenses, like stem cell therapies or targeting senescent cells, may be necessary to counteract damage. Ultimately, the residual effects of radiation highlight that Mars colonization is not merely an engineering challenge, but a profound biological trial. These invisible scars threaten individual health, reduce quality of life, and compromise sustainability. Recognizing and understanding these effects are vital for devising countermeasures. Ensuring safe, long-term habitation depends on addressing these biological impacts, not just physical or mechanical challenges. As humanity ventures further into space, tackling radiation's enduring biological impacts will be essential, not only for survival, but for thriving amid the challenges of a new world. Resilience, innovation, and hope are crucial as we confront these invisible scars, ensuring that the dream of Mars habitation becomes a sustainable reality. The journey to Mars tests human resilience and scientific ambition. While technological advances bring us closer to the red planet, physiological and psychological challenges significantly influence whether astronauts can return and whether they want to. Understanding these factors is crucial since they can determine mission success or failure. Starting with physiological challenges, space is an unforgiving environment. Cosmic radiation is one of the most serious threats. Unlike Earth, protected by a magnetic field and atmosphere, Mars offers little shielding. High-energy particles from solar flares and cosmic rays penetrate spacecraft and habitats. This increases risks of radiation sickness, cancer, tissue, and organ damage. Prolonged exposure can weaken the immune system, making astronauts vulnerable to illnesses, especially far from medical help. Radiation also accelerates degenerative diseases, potentially shortening lifespan or reducing quality of life. If health issues arise, recovery may be impossible without advanced medical care not available on Mars, complicating return plans. Microgravity, or partial gravity on Mars, causes muscle atrophy, bone density loss, and cardiovascular deconditioning. These physiological effects threaten health and impair astronauts' ability to perform tasks like repairs or evacuations. Post-mission, astronauts may require extensive rehabilitation to readjust to Earth's gravity, impacting their capacity to return safely. These physical deconditions undermine physical readiness and safety for return journeys. Besides skeletal and muscular changes, altered gravity impacts bodily functions. Fluid redistribution leads to facial puffiness, nasal congestion, increased intracranial pressure, and visual or cognitive disturbances. Persistent issues could impair decision-making during emergencies, threatening safety and return prospects. The human body's reliance on gravity means these changes can have long-term effects on cognition and health, influencing returnability. Psychological factors are equally formidable. Space isn't just a physical challenge, but a mental test. Isolation, confinement, and separation from loved ones create stress. Missions lasting 2 to 3 years with no rapid escape option heighten feelings of loneliness, anxiety, and depression, which can worsen over time. Being sealed in a small environment with a close team can heighten tensions, sometimes leading to conflicts that threaten team cohesion and mission success. When mental resilience erodes, decision-making suffers, increasing risks for the crew and jeopardizing their journey home. Sleep disruption is common. Without a natural day-night cycle on Mars, days last about 24 hours and 39 minutes. Circadian rhythms falter. Insomnia and fatigue impair cognitive functions like attention, judgment, and problem-solving, crucial for navigation repairs and emergencies. Over time, these sleep disturbances compound, raising the likelihood of accidents and overlooked hazards, making safe return more uncertain. Persistent sleep and mental health issues can destabilize the entire mission. Psychological stress is also influenced by the knowledge that rescue or return may be impossible. This can foster despair, reckless behavior, or decision-making influenced by a desire to remain, especially if mental state deteriorates. The perception of being trapped or stranded influences choices, potentially leading some crew members to opt to stay on Mars voluntarily if risks become too high. Such decisions raise ethical questions about autonomy and safety. Cultural and social issues are critical. Small crews in confined spaces must maintain harmony. Psychological resilience involves not just individual mental health, but team cohesion. Conflict or emotional overwhelm can impair cooperation, slow decision-making, and threaten safety and return plans. Emotional instability might lead to neglecting duties or behaviors that jeopardize the mission or trap crew members on Mars. External environmental stresses further complicate matters. Mars's barren landscape, dust storms, temperature swings, and lack of natural light can intensify feelings of vulnerability and disorientation. Dust storms lasting weeks can obscure visibility, damage habitats, and damage life support systems. These environmental stresses increase mental fatigue, erode morale, and make the idea of returning home seem increasingly distant or even impossible if the environment becomes uninhabitable. Physiological and psychological challenges are deeply intertwined, influencing returnability. Severe radiation sickness, bone fractures, or cardiovascular events might incapacitate crew members during the mission, leaving few options for safe return. Medical emergencies that cannot be sufficiently addressed on Mars limit the feasibility of returning home. At the same time, psychological deterioration can diminish the desire or ability to continue or attempt return. Despair or mental crisis may cause crew members to reject the idea of going back, preferring to remain on Mars if they believe their mental or physical state is better there. The interaction of physical and psychological factors shapes decision-making about mission duration and exit strategies. Planning must consider the possibility that some crew may voluntarily choose to stay if burdens become insurmountable. These scenarios pose ethical and operational dilemmas. Are these choices rational, or are they the result of preventable stresses? The complex interdependence means physical health decline can intensify psychological distress, creating a vicious cycle. An astronaut with microgravity-induced osteoporosis, for example, may experience pain and helplessness, fueling anxiety and depression, which further impair coping ability. Conversely, mental stress can suppress immune function, prolong recovery from physical injuries or illnesses. Developing countermeasures is vital. Physical measures include radiation shielding, exercise protocols, and medical treatments designed to reduce health risks. Psychological support, virtual contact with loved ones, recreational activities, counselling helps foster resilience and cohesion. Habitat designs that mimic Earth environments, with lighting simulating natural cycles or immersive virtual reality, can support mental health. Incorporating these strategies extends the likelihood of safe return. Ultimately, the success of a Mars mission hinges on understanding and mitigating these intertwined challenges. They influence every decision, from mission planning to crew well-being. While technology may bring explorers to Mars, safeguarding human health, both physical and mental, is essential to ensure they can return home. The balance of science, resilience, and human support determines whether these adventurers can truly make it back. The complex interplay of physiological and psychological factors shapes the potential for return, impacting safety and decision-making during every phase of the mission. Their influence underscores the importance of comprehensive preparation and support systems. Addressing these challenges can help ensure that humans not only reach Mars but also find their way back, maintaining the human spirit amid the vast uncertainties of space exploration. Current life support systems, despite technological progress, face significant limitations in sustaining life on Mars. These systems are essential for astronauts venturing into the unknown, but they are far from perfect, illustrating the immense challenges of making Mars habitable for humans. A major limitation is dependence on Earth-based supply chains for essentials like food, water, and oxygen. Although efforts have developed closed-loop systems to recycle resources, technology cannot operate independently over extended missions. Water recycling, while effective, is not foolproof. It requires substantial maintenance, and failures could threaten crew survival. Water treatment involves filtration, purification, and chemical processes, each needing flawless operation. Minor malfunctions might cause contamination or resource depletion, risking dehydration or health issues. Oxygen generation relies on water electrolysis, which depends on sufficient water supplies and reliable systems. On Mars, where water is scarce and often impure, maintaining a steady oxygen supply is challenging. Extracting water from Martian soil and recycling it efficiently is still being developed. These processes must be resilient and autonomous, capabilities still under refinement. Food production faces environmental and resource constraints. Growing food in Martian conditions, low gravity, limited sunlight, high radiation, requires complex agricultural systems. Bioregenerative life support systems such as plant chambers, hydroponics, or algae farms show promise but remain early stage. Most missions rely on pre-packed foods from Earth, limiting duration and increasing payload costs. Challenges include microbial contamination, radiation-induced mutations, pests, and the difficulties posed by Mars' thin atmosphere and frequent dust storms. Radiation shielding presents another obstacle. Solar and cosmic radiation threaten health and damage systems. Protective habitats can employ shielding materials such as regolith layers or specialized alloys, but these add weight and cost. Existing structures are not optimized for long-term radiation protection. Excessive weight hampers mobility and expansion. Failure to adequately shield can expose crews to high radiation doses, increasing risks of cancer, radiation sickness, and genetic damage. Environmental control within habitats is complex. Maintaining stable temperature, humidity, and atmospheric composition requires continuous regulation. Unlike Earth's natural buffers, artificial life support systems must filter contaminants, manage humidity to prevent mold, and precisely control oxygen and nitrogen levels. Fluctuations can cause episodes of off-gassing, pressure drops, or degraded air quality, threatening crew health. Backup systems increase habitat complexity and weight, but are necessary for safety. The integration of all subsystems, water recycling, oxygen generation, food production, and environmental control, is a monumental engineering challenge. Failures in one component can cascade, affecting others. For example, a water recycling failure might influence humidity and air quality, jeopardizing plant growth and oxygen levels. Systems designed with redundancy and fail-safes help, but some failures are inevitable in extreme environments. Power supply remains a key concern. Life support systems depend on reliable energy sources such as solar panels, nuclear reactors, or batteries. Solar power offers abundant energy but is vulnerable to dust storms that can last days or weeks, drastically reducing power output. Inadequate power can cripple life support and threaten habitat safety. Nuclear power offers more reliability but raises safety issues, including radiation shielding and waste management, especially in a fragile Martian ecosystem. Sterilization and contamination control pose additional challenges. Achieving a sterile environment on Mars is daunting. Microbial life from Earth, on equipment, habitats, or within astronauts' microbiomes, risks contaminating the Martian environment and harming human health. Conversely, suppressing all microbes might hinder essential biological processes like soil bacteria that support plant growth. Striking the right microbial balance remains difficult. The size and mass of life support systems are formidable issues. These systems need to be compact, lightweight, and energy efficient for transportation and deployment. Current prototypes tend to be bulky, energy hungry, and resource intensive, making large-scale implementation difficult. As missions extend and become more ambitious, these limitations could become insurmountable with existing technology. While current systems have enabled astronauts to spend months on the International Space Station, transitioning to a sustainable, long-term human presence on Mars involves unresolved issues. Each limitation underscores the need for innovation, resilience, and adaptability. Developing more autonomous, efficient, and integrated systems is critical for overcoming these hurdles. Progress requires pushing beyond current boundaries, creating systems that are reliable, self-sustaining, and capable of functioning in the harsh Martian environment. Advancements in recycling technologies, habitat design, radiation protection, and biological systems are essential. For example, improving water purification, autonomous oxygen production, and reliable food cultivation could support long-term habitation. Innovations in lightweight shielding materials and power sources capable of withstanding dust storms are also vital. Microbial control and sterilization methods will be necessary to prevent contamination and ensure crew health. Creating resilient, fully integrated life support systems capable of operating seamlessly in Mars' environment remains one of the greatest challenges of future space exploration. It demands pushing current engineering, biological, and environmental management boundaries. Continued research and innovation can help overcome these obstacles, paving the way for human civilization beyond Earth. In sum, while impressive progress has been made, current life support systems are still insufficient for permanent colonization of Mars. Technical hurdles, resource independence, environmental stability, radiation shielding, system integration, power reliability, sterilization, and mass reduction are substantial. Overcoming them requires significant advancements, transforming today's science fiction into tomorrow's engineering reality. Only then can the vision of human settlement on Mars become a genuine possibility, turning the red planet into a second home for humanity. Resource scarcity significantly impacts the safety of Mars return missions. Astronauts carry hopes of discovery but face immense logistical and survival challenges. Every resource, water, oxygen, fuel, or food, is precious. When supplies become insufficient, returning home becomes risky. Survival depends on meticulous management, replenishment, and planning. Finite water and oxygen stocks support life support, cooling, oxygen regeneration, and hydroponic food growth. Exhausted supplies before establishing local systems threaten the mission's primary goal, the safe return. Precision in decision-making is essential, balancing safety margins with conservation efforts. Fuel scarcity complicates matters further. Rockets depend on refined propellants, often derived from chemical sources or in situ resource utilization, such as extracting methane and oxygen from Martian ice. These processes are still developing, carrying uncertain reliability. Unexpected fuel depletion makes returning perilous. Crews face the dilemma to either continue risking resource depletion or remain on Mars indefinitely, awaiting unlikely rescue. Resource management is critical for contingency planning. Missions incorporate redundancies, multiple systems, backup supplies, emergency protocols. Still, resources are finite. Overuse in exploration, emergencies, or failures leaves less for re-entry. Return timing depends on reserves, not just to reach Earth but to do so safely. Miscalculations can turn a successful homecoming into disaster. Environmental factors on Mars exacerbate scarcity. Dust storms lasting weeks clog life support and damage solar panels, reducing energy and resource processing. Cold temperatures demand more heating, draining power reserves, water sources are limited, and extracting water remains technologically challenging. System failures or delays in extraction can exhaust supplies faster than anticipated, leaving crews with no options and in a precarious position. Psychological pressures from shortages are significant. When supplies are low, mental health issues, anxiety, fear, despair grow. These impair decision-making and cohesion. A distressed team may struggle to manage crises or ration resources, threatening mission success. Small delays or losses can trigger chain reactions. For instance, a clogged oxygen generator causes oxygen levels to drop, prompting reduced activity and increased stress. Declining morale hampers resource efficiency, creating a vicious cycle. Tight fuel reserves make errors or hesitation during critical maneuvers dangerous. Every minute during entry, descent, and return counts. In situ resource utilization offers hope but remains experimental. Technologies to extract water from soil or produce methane fuel from atmospheric CO2 could provide vital resupply options. However, these systems are unproven at required scales and reliability. Reliance on developing technology adds risk. Failure means stranded crews without replenishment options. Communication delays, 15 to 25 minutes each way, force astronauts to make decisions independently. When facing resource shortages, crews decide whether to push forward, conserve, or abort under intense pressure. Limited real-time guidance increases dependence on training and judgment, making decisions heavily influenced by resource status. Resource scarcity is an existential threat. Unlike Earth, where resources are abundant and renewable, Mars offers none. Every resource must be conserved, sourced, or recycled efficiently. Failure to do so risks turning ambitious plans into failures or tragedies. Addressing resource management is crucial for future Mars exploration. Developing reliable in-situ resource utilization, energy-efficient habitats, and strict conservation protocols will shape mission sustainability. Without these, resource scarcity remains an ongoing threat, turning the goal of safe return into a high-stakes gamble. Neglect could lead to tragedy, making the journey home perilous. Technology plays a vital role in overcoming scarcity. Extracting water from soil, producing fuel from atmospheric gases, recycling waste, all innovations critical for survival. Improving the reliability and scalability of these systems increases chances of safe return. Habitat designs that minimize resource use without sacrificing safety and comfort are equally important. Psychological effects of shortages are also significant. Physical threats are worsened by mental stress. When supplies dwindle, anxiety and depression can impair judgment and cooperation. Supporting mental resilience is crucial. Psychological well-being directly impacts mission success. Redundancy in systems and supplies is essential with constrained resources. Backup methods, emergency protocols, and resource-sharing strategies can buy crucial time. Diversifying water sources or using multiple energy generation methods prevents single points of failure. Such resilience measures help prevent crises caused by unforeseen shortages or system failures. Technological advances in resource production could revolutionize missions. Demonstrating reliable in-situ extraction and fuel generation reduces dependence on slow, costly resupply missions from Earth. Autonomy becomes vital given communication delays and logistical hurdles, making in-situ systems essential for survival. Resource scarcity also raises ethical and operational questions. Deciding how to allocate limited supplies, prioritize crew health, or determine abort thresholds is complex. Well-planned protocols and transparent decision-making are vital to maintain mission integrity and safety under resource constraints. In sum, resource scarcity fundamentally affects mission planning, operations, and safety. It demands innovation, rigorous planning, and resilient systems. As humans venture further into space, mastering resource management is essential. It determines whether astronauts return safely or become stranded. Investing in safeguards and reliable systems brings us closer to safe Mars missions. Neglect, however, can turn success into tragedy, etched into human exploration's history. Progress depends on technological development, strategic planning, and mental resilience. Solving resource management puzzles will define mission success and serve as a reminder that human survival beyond Earth hinges on innovation and adaptation in resource-limited environments. Fundamentally, resource scarcity highlights the challenge of exploration, thriving in the unknown while protecting the journey home. The journey to Mars involves significant technological challenges, with failures that could make returning to Earth impossible. Such failures threaten not only the success of the mission, but could leave astronauts stranded in deep space miles from rescue, relying solely on their training and resilience. A critical system at risk is the spacecraft's propulsion. Modern propulsion, chemical, ion or electric, is complex and precise but not infallible. Mechanical failures such as turbine blade fractures, fuel line blockages, or pump failures could leave the spacecraft unable to decelerate or initiate its return trajectory. If propulsion fails after leaving orbit, the craft couldn't adjust course for return, trapping the crew in orbit around Mars or deep space. Fuel management is vital. The amount of propellant is carefully calculated for launch, landing, ascent, and return. Any leak or gauge error, underestimating fuel use, could mean running out of the critical propellant needed for the return burn. Imagine having a perfect landing site, but no fuel to lift off or perform necessary maneuvers to rendezvous with orbiters. Such failure would condemn the crew to a solo or deadly existence on Mars or in the void between planets. Life support systems are crucial for survival, providing breathable air, water, and temperature regulation. Failures here could be disastrous. A breach in the atmosphere control system could cause rapid air loss, making return impossible without rescue. Malfunctions in water recycling or food systems threaten resource exhaustion. For example, a malfunction in oxygen generation could slowly diminish breathable air, creating a potentially lethal situation with no safe evacuation. Heat shields and descent systems are critical during planetary entry. They must withstand intense thermal loads. A defect, improper deployment, or debris damage could cause the spacecraft to burn up during re-entry, trapping crews on Mars or lost in the atmosphere. Conversely, failure of parachutes or landing gear could result in a crash, destroying the craft beyond repair. These systems are the sole gateway back to Earth once the crew lands. Onboard power systems are vulnerable. Spacecraft depend on solar panels and batteries to operate communication, science equipment, and life support. Damage from solar storms or debris can disable these systems, including communication channels. Without communication, the crew cannot send distress signals or get guidance, trapped in a silent limbo with dwindling resources and no help in sight. Communication is vital for navigation, diagnostics, and psychological reassurance. If communication systems fail, even temporarily, crews risk losing access to guidance or expert advice, impairing troubleshooting. An extended blackout might lead to risky emergency decisions such as attempting repairs without guidance, risking further damage or incapacitation. Life-critical software systems are another potential failure point. Spacecraft rely on sophisticated software to manage guidance, navigation, and control. Glitches, triggered by cosmic radiation or unforeseen events, could cause deviations or loss of control. Such scenarios could be catastrophic, making return impossible if the crew cannot manually override or repair the software remotely. Radiation shielding is crucial beyond Earth's magnetic protection. Cosmic rays and solar particle events pose significant threats. Shield failure or unexpected solar storms could expose astronauts to lethal radiation doses. While not directly preventing return, radiation damage can impair electronics or cause radiation sickness, affecting crew decision-making and operational capacity. Damage to electronics could cascade into life-threatening emergencies. The physical integrity of the spacecraft is also a concern. Designed to endure launch stresses, space travel, and atmospheric entry, damage from micrometeoroid impacts or material fatigue could weaken the structure. Breaches or ruptures might cause depressurization or system failures, leaving the crew vulnerable and stranded. All these failure modes highlight the fragile complexity of human space exploration. Every component must operate flawlessly to ensure safe return. Venturing into the Martian frontier involves unavoidable risks, but rigorous preparation and understanding of failure points are central to mission planning. Once launched, the stakes become existential. Failure beyond repair means the door back to Earth closes forever, and humanity confronts space's silent vastness alone. The possibility of system failure underscores the importance of redundancy, repairs, and contingency plans. Engineers must mitigate risks through design, testing, and backup systems. Crew training emphasizes managing failures and improvisation when systems malfunction. The balance of risk and ingenuity defines mission success and safety. Early detection and maintenance are vital. Recognizing issues before escalation allows crucial corrective actions. Regular diagnostics and remote troubleshooting are essential, but if critical failures occur unexpectedly, the crew must respond swiftly, often with limited tools and in constrained space environments. Safeguarding the return involves addressing every potential failure mode. This includes mechanical components, fuel supplies, software, and shielding. The stakes are the lives of astronauts and the future of human exploration beyond Earth. Ensuring every system functions reliably is fundamental, as a single failure could end the journey, leaving astronauts stranded. Understanding and minimizing these failure modes remains central to mission planning. Every system must be designed with resilience and redundancy, knowing that once the journey begins, fallback options are limited. Human resilience and ingenuity are tested, and success depends on meticulous preparation. The harsh reality is that every spacecraft system must function flawlessly. A critical failure could mean the end of the mission, leaving astronauts stranded or worse. The journey to Mars is as much a test of technological prowess as it is of our ability to anticipate and manage failure. Failures are not mere technicalities, they are existential threats. Each component must be scrutinized, tested, and maintained to prevent catastrophe. As humanity reaches for the Red Planet, these challenges highlight the importance of engineering, planning, and resilience. The stakes are high and risks significant. Every step forward must include safeguards to prevent failures that could doom missions or astronauts. The Mars adventure must prioritize safety, reliability, and recovery capacity, because once systems falter beyond repair, the door back to Earth closes forever. The future of human spaceflight depends on understanding, preparing for, and managing these failure modes. Only through meticulous planning and resilient systems can we hope to return safely from Mars, transforming an old dream into a sustainable reality. Contemplating a round-trip journey to Mars reveals staggering complexities. Logistical and technical challenges create an intricate web that makes returning home seem not just difficult, but perhaps infeasible with current technology. Every phase – planning, launch, landing, surface operations, departure, and return – requires meticulous precision, seamless coordination, and foresight that surpass current capabilities. These challenges impact mission feasibility and shape debates about the sustainability of human exploration on Mars. First, the sheer volume of supplies needed is monumental. Unlike Earth, where resupply missions can be frequent, Mars missions must be nearly self-sufficient. Crew needs food, water, oxygen, medical supplies, spare parts, scientific instruments, and life support systems, all transported from Earth. This load increases spacecraft mass, requiring larger rockets, more complex logistics, and higher costs. Every additional kilogram raises payload and fuel requirements, exponentially escalating expenses. Resupply logistics become even more complicated with delays or unforeseen obstacles. Launch windows to Mars occur roughly every 22 months. Missing a window could leave astronauts with dwindling supplies and mounting stress, risking mission failure. This narrow window demands impeccable timing and coordination, but introduces vulnerabilities. Small miscalculations or disruptions can have outsized effects. Surface operations pose another challenge. Once on Mars, astronauts must establish habitats and systems supporting life independently. They need to generate water, produce oxygen, and manage waste amid extreme temperatures, pervasive dust storms, and high radiation. Preparing for departure requires assembling and fueling spacecraft, ensuring systems operate properly, and coordinating launch timing. Failures or oversights could jeopardize the return. Fuel logistics are among the most daunting. To make a safe return, crews must carry enough propellant or produce it on site via in-situ resource utilization, ESRU. While promising in theory, ESRU remains experimental and unproven at the necessary scale. Producing fuel locally involves harvesting and converting Martian resources under dust storms, temperature swings, and radiation, conditions that impose significant technical hurdles. Until mature, missions must carry large amounts of fuel from Earth, adding weight and risk. Timing and coordination of launch windows are crucial due to celestial mechanics. Slight miscalculations or delays can mean missing optimal windows, forcing crews to wait on Mars for extended periods, which increases risks related to supplies, mental health, and system reliability. Conversely, rushing launches or poor planning could endanger safety and fuel efficiency, potentially causing mission failure. Communications delay further complicates return logistics. Signals can take up to 20 minutes each way, making real-time troubleshooting impossible. Ground control cannot intervene instantly during emergencies, requiring astronauts to diagnose and repair systems with limited support. This necessitates redundancy in critical systems and crew members with advanced technical skills. Incorporating spare parts, tools, and backup systems increases payload mass, raising costs and complexity. Supporting crew members during the return involves additional logistical hurdles. Spaceflight subjects them to prolonged stress, fatigue, and psychological strain. Ensuring sufficient supplies, food, water, medical provisions, and entertainment for months requires extraordinary planning. These resources must be balanced against payload constraints and fuel limits to avoid health issues or mission compromise. Any logistical failure could jeopardize their well-being or mission objectives. Safe re-entry to Earth introduces another set of challenges. Precise calculations are necessary for the trajectory, heat stress management, and safe landing. Failures in planning or mechanical systems could result in crashes or severe damage. Designing reliable heat shields, landing systems, and backup procedures adds further complexity and cost, yet is essential for crew safety. Financial considerations pose an overarching challenge. Launching multiple spacecraft, maintaining systems, producing fuel on Mars, and ensuring redundancies all incur enormous expenses. The potential loss of expensive hardware or lives amplifies risks, often leading to delays or cancellations. Continuous maintenance, resupply, and contingency planning require massive investment. Insurance costs rise, and funding may dwindle, threatening mission viability. Beyond technical and financial hurdles, logistical constraints influence broader exploration planning. The need for coordination, risk management, and contingency procedures may drive future missions toward longer stays or more autonomous surface operations. Current technological limitations could push reliance on in-situ resource utilization, robotic assistance, and advanced automation to manage failures without Earth intervention. Massive payloads, narrow launch windows, resource limits, complex coordination, and timing constraints form almost insurmountable barriers to safe, reliable return journeys as of today. Overcoming these hurdles demands breakthroughs in propulsion, resource processing, autonomous system reliability, and life support durability. Until such innovations occur, returning from Mars remains an immense challenge. Many experts question if current approaches can ever guarantee a safe, assured return. Every component, from launch, fueling, navigation, repair to re-entry, must function flawlessly. Any failure or slip can have catastrophic consequences. The logistics involved require a finely tuned balance. Missteps are costly or deadly. These complexities highlight a stark reality. Without revolutionary technological advancements, returning from Mars may be impossible. The logistical labyrinth, vast, intricate, and unforgiving, sets a high bar that we are only beginning to understand and aspire to conquer. In summary, the combination of payload mass, limited launch windows, resource constraints, complex coordination, communication delays, and technical challenges makes a reliable return journey extraordinarily difficult. Breakthroughs are needed in multiple fields before a truly feasible Mars return mission can be realized. Until then, the risks and logistical hurdles serve as sobering reminders of how daunting interplanetary travel remains, especially the challenge of returning home safely. The question of whether it is ethically justifiable to send humans to Mars with no promise of return immerses us in moral philosophy, risk assessment, and human aspiration. It sparks debate among scientists, engineers, and society, prompting us to consider our values, beliefs, and ideas of progress. Different perspectives enrich this discussion. Scientists seek cosmic knowledge, explorers are driven by curiosity and the desire to venture into the unknown, while families and communities worry about loved ones embarking on risky, uncertain journeys. The core question is whether it is ethical to prioritize knowledge and human expansion when the risks are so great that returning safely can't be assured. A strong argument in favor of one-way journeys appeals to human curiosity. Throughout history, humanity has pushed boundaries, sailing oceans, exploring continents, diving into the ocean's depths, ascending the skies. Each act of exploration involved uncertainty and peril, yet greatly expanded our understanding. Colonization of Mars isn't just about establishing a new society. It's about reaffirming our drive to explore, learn, and transcend Earth's limits. From this view, risking a one-way trip is a step in human evolution, a bold leap motivated by responsibility to explore, to ensure our survival should Earth become inhospitable, and to achieve goals once thought science fiction. If exploration only occurs where safety is guaranteed, have we limited ourselves? Are we playing it too safe, confined within comfort zones? Taking risks pushes the potential of humanity and aligns with our innate desire to advance. Yet, the reality of risk is stark. Dangers are real. Lethal radiation, microgravity's effects, psychological strain, limited resources, technical failures, all threaten survival. Sending someone on a one-way mission isn't just risky, it risks death, with rescue options nearly non-existent. Is such a risk ethically permissible? Ethical theories like consequentialism weigh potential benefits, scientific breakthroughs, technological progress, inspiration against costs. But benefits are distant, collective, and intangible, making balancing them against the individual's right to safety complex. From a deontological stance, which emphasizes duties and moral rights, sending someone on a one-way trip might violate their dignity and their right to life. Every person has intrinsic value. Risking their lives without hope of rescue challenges moral principles of respect. But if participants give informed, voluntary consent, does that make it ethical? Or does the extreme nature of the risk invalidate consensual agreement? The absence of an escape route might fundamentally undermine the morality of such acts. Society's view adds another layer. How do we value those willing to undertake these journeys? Might endorsing one-way trips create a heroism narrative that glorifies risk-taking and diminishes safety? What message does this send to future generations, prioritizing progress over prudence, ambition over ethics? The cultural implications matter deeply. Justice and fairness concerns are also critical. Who should volunteer for one-way missions? Would selection favor privileged individuals who can accept the risks? Could it lead to exploitation, pressuring or coercing individuals for the collective benefit? How do we ensure voluntary, informed consent? And, in tragedy, what obligations does society owe to explorers and their families? These questions highlight moral responsibilities and societal values. Responsibility itself becomes central. If risks are overwhelming, do we have a moral obligation to prevent such missions? Or do we support human curiosity and exploration, even at great personal risk? Is it ethical to promote endeavours with a high likelihood of loss, perhaps viewing them as necessary for progress? Or is doing so callous and patronising, neglecting the moral weight of potential tragedy? The debate also revolves around individual autonomy versus collective responsibility. Respecting autonomy suggests allowing informed volunteers to accept risks if they find meaning in the journey. Conversely, the collective duty to prevent harm might argue against risking lives in such dangerous missions. Balancing these principles is complex but essential. Historically, high-risk pursuits, for instance, early polar exploration or space missions, were often driven by destiny or national pride. Today, our ethical frameworks urge us to scrutinize whether we understand the profound implications of these risks and whether the potential rewards justifies them. Scientific and societal gains must be weighed heavily against human costs. Ultimately, the ethics of one-way Mars missions are deeply tied to our values, conceptions of progress, and sense of moral responsibility. It asks whether the pursuit of knowledge justifies sacrificing individual lives and if such endeavours genuinely reflect our moral judgment or reckless ambition. The conversation extends beyond science into the core of what kind of species we aspire to be. Are we committed to responsible boundary pushing, respecting individual rights and dignity? Or are we willing to prioritise collective exploration at the risk of moral integrity? These questions resist easy answers, but invite reflection on whether our cosmic ambitions align with our moral standards. They challenge us to think carefully about the ethics shaping our future in space. As humanity advances towards sending humans beyond Earth's confines, grappling with the morality of no-return missions is more than abstract philosophy. It's vital to ensure our pursuit of the stars aligns with the values that define us as a moral species. The debate remains unresolved, but its importance is clear. We must consider whether exploration justifies ending lives without safety, or whether profound risks demand more cautious, values-driven approaches. Ultimately, the decision reflects who we are, ambitious explorers or cautious custodians of moral integrity. The implications for humanity, if Mars colonization becomes a one-way journey, are profound, touching our core identity, values, and future as a species. It challenges us to confront difficult truths about our ambitions and capacity for sacrifice, reshaping our views on exploration, risk, and responsibilities toward the unknown. First, such a mission would redefine what it means to be explorers. Historically, explorers risked and sometimes sacrificed their lives, driven by curiosity and a desire to expand human horizons. If Mars is truly a destination from which no one returns, future pioneers would not seek personal fame or scientific accolades, but act as custodians of humanity's lineage, safeguarding our survival far from Earth. Their journey would be a leap into the unknown, knowing they may never see Earth again. This elevates the narrative from conquest to devotion, volunteers embodying humanity's resilience, enduring hardships for our collective future. This scenario also raises questions about society's psychological and moral fabric. Would we have the courage to support missions where the risks are so high that return is impossible? What societal structures, cultural values, and support systems are needed to sustain the mental well-being of those willing to take such risks? Volunteers would require extraordinary resilience, mental toughness, and unwavering purpose, knowing their sacrifices might be total. Their families, communities, and humankind at large would bear the emotional weight, fostering a shared sense of destiny but also profound loss. The emotional toll could echo across generations, reminding us that pursuit of knowledge can come at costs far beyond immediate mortality. Another layer involves the ethics of these one-way missions. If individuals go with the understanding they may never return, are they truly free to choose? Could altruism, ambition, or desperation override doubt and fear? How do we balance our duty to expand human civilization against potential exploitation or coercion? Critical questions include ensuring those who embark are fully informed and their autonomy respected. These moral issues would influence policy and society, prompting humanity to develop new principles about exploration, sacrifice, and responsibility toward those venturing into space. The long-term implications for human civilization are staggering. Earth faces challenges such as climate change, resource depletion, geopolitical tensions, and possible catastrophe. A one-way Mars colonization could serve as planetary insurance, ensuring survival even if Earth becomes inhospitable. A resilient colony might become a seed for future generations, an evolutionary milestone. Yet, it would push us to develop support technologies for extreme environments, closed-loop ecosystems, resource utilization, autonomous systems capable of supporting life over generations. Advances in these areas could also benefit Earth in addressing environmental crises through sustainable practices, renewable resources, and resilient infrastructure. This concept complicates our notions of progress. Traditionally, exploration measures success by discoveries, territory, and scientific achievements, generally with clear risks and returns. Now, success is less about immediate gains and more about endurance, resilience, and survival against impossible odds. Achievement may be defined by humanity's capacity to adapt and persist, with the legacy of pioneers carrying forward long after they are gone. The focus shifts from physical exploration to existential resilience, survivors of an extraordinary challenge. Philosophically, this trajectory prompts a reassessment of human purpose. Are we explorers and settlers of new worlds, or preservers and enrichers of human experience? If Mars becomes an act of sacrifice, an eternal migration, then pushing boundaries through risks and hardship becomes a testament to the human spirit's tenacity. Such endeavors might inspire future generations, viewing setbacks as essential elements of our quest for meaning, growth, and evolution. These shifts would also reshape international relations and geopolitics. If Mars becomes a one-way destination for selected explorers, who controls the effort? Would efforts be international collaborations or dominated by a few advanced nations? Ethical questions about who goes and who stays would influence geopolitics, risking inequalities if resources and opportunities are limited. Wealthier nations or individuals could monopolize space exploration, creating new forms of inequality. Conversely, humanity might seek collective sharing, risk, knowledge, and responsibility, forming new models of global cooperation. Such choices could shape geopolitics for decades, emphasizing the importance of equitable stewardship in space endeavors. Accepting a one-way journey signifies understanding that space exploration may often involve sacrifice rather than safety. It embodies a daring legacy, redefining humanity as pioneers willing to leave everything behind to endure and expand beyond Earth. It is about building a future where some make the ultimate sacrifice for the survival and growth of human consciousness across the cosmos. In this new chapter, the question extends beyond reaching Mars to what future humanity will build while some stay behind. The journey becomes an act of deep commitment, a testament to resilience, hope, and the drive to see the universe as a canvas for defining human destiny. The true challenge is not how many can go, but how prepared we are for a future where some of us remain, steadfast and resilient for generations. We would be writing a new story of mankind, one where the journey is about enduring legacy, not just return. Ultimately, embracing a one-way mission transforms our perspective on exploration. It shifts our focus from conquest and discovery to resilience and survival. It demands a re-evaluation of our values, prioritizing collective sacrifice, long-term sustainability, and the courage to face the unknown regardless of immediate return. Humanity's future might be one where some of us leave everything behind, not just to reach new worlds, but to forge an enduring legacy, a testament to our spirit and our desire to expand beyond our limits. The responsibility toward astronauts who may never return from Mars involves profound ethical considerations. It's a complex issue with no simple answer, but demands our full attention as humanity ventures into space, aware that exploration carries irreversible costs. Responsibility is rooted in moral duty, scientific obligation, and societal values. Going to Mars is more than engineering. It's venturing into the unknown, challenging our understanding of caring for explorers. These pioneers face risks: radiation, microgravity health effects, psychological strain, technical failures that are often unprecedented and beyond our control. Despite advances, some astronauts may not return. So, what are our responsibilities if that happens? Is providing care, support and respect during and after the mission enough? Or does responsibility extend into fundamental commitments to exploration and human dignity? First, responsibility means ensuring astronauts are fully informed before risking their lives. They must understand every danger: radiation, life support limits, uncertainties, with honesty and transparency. This respects their autonomy and agency, enabling truly informed consent. Portraying only positives isn't enough. Full disclosure of risks allows them to make educated decisions. Respecting their choices involves providing all necessary information, acknowledging potential loss, and honouring their willingness to undertake such perilous journeys. Beyond informed consent, responsibility involves deploying the best possible technology, procedures, and support systems to reduce risks. This calls for relentless innovation, developing fail-safe tech, rigorous training, and contingency plans. Our obligation is to push safety boundaries without compromising mission goals. We must learn, adapt, and invest in research to safeguard astronauts against unpredictable dangers. When risks cannot be fully mitigated, responsibility shifts to managing the aftermath. What happens if an astronaut is lost, injured, or left behind? Respecting sacrifice entails honouring those who venture into the unknown, treating their memory with reverence, supporting their families and colleagues, and continually improving safety measures. Their bravery and curiosity are remarkable, but our response must be rooted in humility and compassion, not complacency. We owe it to them to pursue safer missions and recognise their commitment through moral responsibility, not resignation to tragedy. The moral weight of Mars exploration also raises questions about our duty to future generations. Planning missions with possible loss prompts us to ask, are we fulfilling societal responsibilities? What is the long-term impact on families, communities, and society supporting these explorers? We need a culture of care, protecting not only astronauts' safety, but also the values that define humanity. Their journeys symbolize collective aspirations, and thus impose a moral obligation to approach their missions and potential sacrifices seriously. Responsibility involves reciprocity. Honoring those who accept risks includes policies that recognize their sacrifices, financial support, mental health resources, societal acknowledgement, and ensuring their contributions lead to societal benefits. Scientific breakthroughs, technological progress, a deeper understanding of human resilience. Their willingness to explore should inspire progress, even if they do not return. Accountability is vital. When mishaps occur, responsibility requires transparency and acknowledgement. Clear accountability among mission planners, engineers, political leaders and funders is essential. When accidents happen, honesty breeds trust. Cover-ups or shirking responsibility undermine integrity, especially in high-stakes endeavours like space exploration. Ethical considerations extend beyond safety. As we consider colonising Mars, we must reflect on our duty not to repeat past mistakes, exploitation, environmental destruction, neglect. We bear a moral responsibility to respect Martian environments and potential non-human life forms. Our curiosity must be balanced with caution, humility, and respect for other worlds. Protecting planetary integrity and potential life is an essential aspect of responsible exploration. All these points reinforce a core truth. Responsibility toward astronauts who might not return extends beyond safety protocols. It's about honouring human agency, dignity, and moral accountability for the risks we impose. It's about fostering a culture rooted in care and respect, acknowledging sacrifices and the trust placed in us to safeguard them amid uncertainty. To uphold this responsibility, we must continuously ask, are we doing all we can to ensure their safety? Are we honest about dangers? Are we prepared to support and honour their sacrifices? Are we learning from mistakes so that, if tragedy occurs, we respond with compassion and integrity? These questions must guide us because we owe that moral duty to brave souls looking up at Mars, dreaming of reaching it. Responsibility also involves long-term thinking, considering moral, environmental and societal implications of interplanetary travel. As we push boundaries, we must avoid repeating injustices, exploitation, neglect, environmental harm, and apply lessons learned on Earth. We have a duty to safeguard not only explorers, but also the environments of other planets and potential life forms. Respecting planetary environments and maintaining humility in our pursuits ensure ethical and responsible actions. This ethical stance encompasses a commitment to humanity's progress, based on moral integrity and respect for other worlds. The pursuit of knowledge and exploration must be matched with cautious stewardship, humility, and the recognition of our responsibilities as custodians of Earth and other celestial bodies. In summary, responsibility toward astronauts who may not return involves more than safety. It includes safeguarding their human dignity, supporting loved ones, learning from failures, and respecting environments encountered. It's about cultivating moral accountability, transparency, and care, acknowledging risks and sacrifices in the name of progress. Our duty is to balance curiosity with caution, ambition with humility, and progress with integrity. Ultimately, it's about valuing human life, honouring exploration's spirit, and conducting this venture with compassion, respect, and responsibility. This moral commitment is ongoing. Are we doing everything possible to protect them? Are we truthful about risks? Do we support their sacrifices? Are we acting ethically in failures or tragedies? These questions define our humanity and our respect for those daring to reach for the stars. Their courage inspires us, and our actions must reflect our deepest moral commitments to care for their lives, honour their daring, and uphold the values that make exploration meaningful. Responsibility is more than preventing death. It's about valuing human life, fostering discovery, and fulfilling our moral duty to those venturing into the unknown. We must ensure that in our pursuit of new worlds, we never forget the humans behind the mission, the explorers whose dreams, sacrifices, and lives propel us into the future. As we contemplate one-way missions to Mars, profound philosophical questions emerge, queries challenging our understanding of human identity, purpose, and legacy. Entering this realm, we confront mortality and the impermanence of individual existence. Human life is traditionally bound by birth and death. Our stories, achievements, and memories fade over time, yet they endure through generations, culture, and knowledge. But what if the journey is designed to be permanent? When individuals choose, or are chosen, to face an uncertain, often hazardous fate, knowing they might never see Earth again, does their mortality become an act of defiance? Is it a statement that human curiosity and presence matter enough to justify eternal effort? Or does it diminish life's fleeting beauty, turning existence into a transient ripple in an indifferent cosmos? Similarly, if humans voyage to Mars without expectation of return, how does that shift our conception of legacy? On Earth, influence persists through families, art, discoveries, civilizations, a narrative woven over centuries of human ingenuity and resilience. But on Mars, with communication delays or severance, and with no guarantee of carrying stories or cultural artifacts back, does legacy change? Perhaps it becomes about establishing a living colony, an imprint in Martian soil, acting not just as exploration, but as a new chapter of humanity existing independently of Earth's memory. This prompts us to consider human identity itself. Are those taking these one-way journeys still truly human, or do they transform into pioneers of a new consciousness? When individuals commit to living on Mars, potentially for generations, their identities are influenced by the physical, psychological, and social realities of their environment. Their self-perception might shift due to microgravity, radiation, and isolation. Traditional bonds, family, community, cultural continuity may be altered. They might become more introspective or develop novel social structures. From this perspective, colonization, especially when irrevocable, raises the question: does it redefine what it means to be human? Is humanity a fragile shared heritage, or can it evolve through environmental and social remaking? If future generations inherit Martian colonies, if the original pioneers become ancestors of a new human lineage, what aspects of their identity remain? Could they become a new species shaped by Mars conditions? And if so, what does that imply about human essence itself? Are we bound by genetics, or by consciousness, culture, and choice? Another layer of philosophical inquiry involves purpose and meaning. Why venture into the unknown with the knowledge that efforts may amount to a single, unreturnable chapter? Is it hubris, a desire to transcend earthly limits, or an intrinsic quest for meaning beyond survival? When pioneers accept they might never see Earth or loved ones again, what motivates them? Knowledge, survival, a deeper existential drive to ensure humanity's continuity in an indifferent universe? Their sacrifice could symbolize human resilience or challenge traditional notions of a worthwhile life. Memory and storytelling also raise questions about legacy. On Earth, histories are passed through oral tradition, writing, digital archives. But on Mars, especially initially, how will stories be told? Will future colonists document their origins? Will they record struggles, triumphs, failures to stand the test of time? Or will the environment and focus on daily tasks lead to cultural memory fading? If memories fade, does that diminish the human experience, or simply redefine what it means to be part of a broader ongoing story? This links to questions of intentionality and sacrifice. When individuals go on these missions, often knowing they might never return, moral and ethical considerations arise. Are they heroes, sacrificing their futures for humanity's progress, or explorers driven by curiosity and transcendence? Perhaps both. What does this reveal about human nature? That we undertake ventures fraught with danger, even death, for higher purposes. If they succeed, what kind of heroes will they be? Those daring to cross the ultimate frontier, or martyrs paying the highest price for knowledge? The implications for future generations deepen the philosophical landscape. A Martian colony might serve as the seed of a new civilization, an independent, self-sustaining society. How do the choices of ancestors influence descendants? Will they see themselves as continuing Earth's legacy, or as pioneers forging a new identity? Do they bear the responsibility of preserving Earth's history, or are their primary obligations to develop a distinct Martian culture? And if they do, what does that mean for human universality? Is there something inherently human about consciousness and morality, or do these qualities evolve with environment and circumstance? Contemplating these ideas leads to an overarching concern: purpose itself. For many, a one-way journey to Mars symbolizes hope, one that suggests human life can extend beyond Earth, that curiosity and resilience can forge new worlds. Yet, it also confronts uncomfortable truths about mortality, impermanence, and values. Does leaving a legacy justify the risks? Does choosing to go, knowing there's no return, elevate the human spirit into new realms of meaning? Or does it reveal a deep-seated fear of death, propelling us to leave artifacts of ourselves, even on distant planets? These questions aren't limited to individual journeys, but reflect broader themes: our collective purpose, capacity for sacrifice, consciousness, and long-term human evolution. They prompt us to ask whether the greatest legacy might be the stories we tell ourselves, the cultural footprints we leave, or simply the act of daring to explore, even with no hope of return. Ultimately, they challenge us to consider what it means to be human in a universe of infinite possibilities and how we define our place within it. The responsibility resting on today's space agencies as we approach sending humans to Mars is monumental. Their duties now extend beyond technological development to encompass ethical stewardship and foresight, laying the groundwork for future Martian inhabitants. These agencies aren't just designing ships or plotting trajectories, they're establishing the foundation for life on another planet. Primarily, their responsibilities include ensuring the safety, health, and well-being of astronauts. This involves creating a self-sustaining environment capable of supporting human life in a hostile alien world. Life support systems must operate reliably for years, and psychological support structures are needed to help individuals cope with isolation and distance from Earth. Agile planning must incorporate redundancies and contingency plans, as rescue options become nearly impossible once a voyage begins. Safety isn't only about immediate survival. It extends to long-term health concerns like microgravity effects, radiation exposure, and psychological challenges of isolation. Agencies are tasked with extensive pre-mission research to understand and mitigate these risks, developing shielding strategies, habitats that reduce psychological stress, and ensuring nutritional and medical needs can be met independently for decades. Beyond physical safety, an ethical responsibility exists regarding the environment and future community on Mars. Agencies must establish guidelines to prevent contamination, protecting both Earth and Mars, and respect the intrinsic value of the Martian environment. The aim is to avoid reckless exploitation and ensure Mars remains a place for scientific inquiry and exploration. Sustainability is crucial. Long-term habitation requires technologies that minimize resource depletion and environmental impact. Developing closed-loop life support systems, renewable energy sources, and in-situ resource utilization, converting local materials into water, oxygen, or building supplies is essential. These moral and technical challenges highlight that neglecting planetary health could leave future generations with a scarred Mars, not a new frontier. In essence, space agencies are entrusted with pioneering a fragile civilization rooted in responsibility, respect, and foresight. Their decisions influence whether future Martians thrive or endure degraded environments caused by hurried efforts or poor planning. They must establish governance, legal and ethical frameworks to keep human activity on Mars fair, transparent, and respectful of potential inhabitants. Another key responsibility is education and transparency. Open communication fosters trust among the public, scientists, policymakers, and future settlers. Honest updates about risks, progress, and setbacks promote shared ownership of this historic enterprise. Diverse voices, especially marginalized groups, must be included in dialogues about colonization, environmental stewardship, and morality related to extraterrestrial life and human presence. Furthermore, agencies must promote international collaboration, emphasizing Mars as a shared human achievement rather than national or corporate territory. This involves diplomacy and setting standards for peaceful exploration, equitable resource sharing, and adherence to space law, which views celestial bodies as part of a global commons. Foresight is essential, anticipating societal impacts long-term. Future perceptions of current efforts depend on responsible actions today. This includes investing in education, creating frameworks for regenerative practices, and cultivating respect for extraterrestrial environments and potential life forms. These actions reflect a commitment to moral and cultural legacies we leave behind. Ongoing and adaptive responsibilities mean policies and practices must evolve with technological advancements. The journey to Mars is not a single event, but a continuous process of learning and adaptation. Agencies need to remain flexible, revise standards based on new scientific data, and solve unforeseen challenges, all while maintaining accountability. Preparedness to adjust is vital for sustainable progress. Every action by current space agencies will have lasting effects. Their choices extend into moral and societal realms, shaping humanity's future on a new world. They are caretakers of a grand experiment, a human step beyond Earth, and they bear the obligation to do right by future explorers, ensuring they inherit a world of opportunity, harmony, and respect. Not one marred by neglect, depends on responsible stewardship. Fostering a culture of responsibility, ethical awareness, and foresight is essential. space agencies must prioritize environmental preservation, minimize waste, and prevent harm. They should advocate for international cooperation, recognizing that space is a shared domain requiring collective governance and mutual respect. Such collaboration upholds fairness and shared benefits, keeping Mars open for future generations. The moral duty of these agencies involves balancing technological progress with ethical considerations. This includes establishing guidelines for environmental protection, planetary protection protocols, and biosafety measures. Acting prudently to avoid contamination and ecological damage is paramount. Ensuring future settlements are sustainable and resilient by building adaptable habitats and infrastructure is crucial, considering evolving conditions and resource availability. Transparency is also vital. Sharing information openly with the global community builds trust and collective responsibility. Acknowledging risks, setbacks, and uncertainties fosters honesty and shared purpose. Such openness invites diverse perspectives and encourages inclusive decision-making, strengthening the moral fabric of this project. Spatial and legal frameworks governing human activity must be carefully crafted. International cooperation, peace, and adherence to space law principles are critical, ensuring that no single entity claims sovereignty or exploits resources irresponsibly safeguards humanity's collective interest. This shared vision promotes peaceful exploration and prevents conflicts over extraterrestrial resources, respecting Mars as a heritage for all humankind. In considering future societal impacts, agencies must think long-term. Fostering public engagement and inspiring future generations is vital. Investing in STEM education, promoting planetary stewardship, and cultivating a global respect for extraterrestrial environments shape how humanity perceives its role as a spacefaring civilization. The ongoing nature of this commitment requires vigilance. As science and technology develop, so must the policies governing their use. Flexibility, continuous learning, and willingness to revise practices are essential. Agencies need to listen to scientific insights, adapt strategies, and address unforeseen challenges with humility and accountability. Ultimately, the steps taken today define the legacy for future explorers. The moral and practical responsibilities of space agencies extend beyond logistics. They lay the moral groundwork for humanity's presence on another planet. Their decisions influence whether future generations inherit a thriving, respectful, and sustainable Martian environment. Building this future demands unwavering dedication to responsibility, respect, and foresight. Embodying these principles is critical for honoring humanity's ambition to explore and inhabit Mars responsibly, ensuring the venture benefits all humankind. The potential permanence of Mars settlements fundamentally reshapes how we consider responsibilities and ethical stances toward these distant worlds. It's no longer just about short-term exploration or establishing temporary bases. It's about creating societies that could endure for generations, perhaps centuries. This shifts the conversation from adventure to moral obligation, forcing us to confront questions about our role as stewards of another planet and whether our actions today will safeguard or threaten these nascent civilizations. When we think about permanence on Mars, we must ask, what legacy are we leaving behind? Are we prepared to implement policies that protect and preserve Martian environments? Or will we treat it as a blank canvas for human activity without regard for ecological or ethical consequences? Unlike Earth's billions of years of evolution shaping complex ecosystems, Mars presents a pristine, fragile world that might host no familiar life forms. If settlements become permanent, we acquire a moral responsibility similar to that of parents to their children, to nurture rather than exploit, to protect rather than pollute. This enduring presence compels us to rethink our ethical principles profoundly. On Earth, debates often revolve around sustainability, balancing human needs with ecological integrity. On Mars, the stakes are heightened. The environment is vulnerable, and significant alterations might be irreversible. Introducing terrestrial microbes or releasing pollutants could cause cascading effects, disrupting native conditions or future ecosystems we might attempt to cultivate. Our moral dilemma becomes, should we preserve Mars in its pristine state, or are we justified in transforming it into a human habitat? Every decision resonates into eternity on this distant landscape. Adding complexity are the ethical implications of colonization itself. If settlements become permanent, they evolve into new societies with their own norms, laws, and morals. Do we have the right to impose Earth's values on these off-world communities? Or should we allow Martian inhabitants, if and when they develop consciousness and identity, to determine their destiny? While initial efforts might focus on survival, fundamental questions about sovereignty and autonomy arise. How much do planetary bodies belong to humanity, and when do they deserve independence? The permanence of Mars also raises sensitive issues about resource utilization. The concept of planetary resource rights is a new frontier. If Mars is viewed as a resource for minerals or materials to support Earth or fuel space exploration, we tread a fine line. Is it ethical to deplete resources that might hold future scientific or ecological value? What about disrupting undiscovered microbial life? Should we develop ethical frameworks recognizing Mars as a space with inherent worth beyond just resources? A further dimension involves our moral obligations to future generations, both on Earth and Mars. Settlements could be passed down as legacies, akin to property or inheritance. What responsibilities do we have to ensure their sustainability? Do we have a duty to prevent environmental degradation, similar to Earth's struggles? Is it moral to transform Mars into a new home, even with irreversible changes? These questions challenge us to weigh immediate benefits against long-term impacts and consider the integrity of future colonies. Many argue that enduring Mars settlements could serve as safeguards against Earth's threats, climate change, pandemics, conflicts. From this perspective, establishing resilient colonies is an act of moral foresight. But even this pragmatic view carries risks. Embedding ourselves into another planet's terrain might cause environmental harm and threaten our moral integrity. Are we justified to create a new space home, or should we focus on repairing Earth's damage first? Respect for the intrinsic value of worlds beyond Earth compels us to question our motives. Long-term colonization demands ongoing governance, resource management, and moral decisions spanning generations. Who will be accountable? Will future inhabitants have a say in managing their environment? How do we embed principles transcending individual or political interests, ensuring just, equitable, and sustainable norms? These questions highlight the importance of designing ethical frameworks adaptable over time to accommodate evolving values and circumstances. When considering ethics and permanence, we must also reflect on our biases. Do we project earthly morals onto Mars, assuming they will remain static? Future settlers may develop different values shaped by new environments and experiences. We should plan policies flexible enough to respect potential moral evolutions, revisiting them as colonies mature. Ethical principles should be open to change, acknowledging that off-world societies might craft their own moral narratives. The permanence of Mars settlements might also alter our view of human identity. What does it mean to be human on another world? Culture, morality, and even biology could change over time. As landscapes evolve, so might our understanding of ourselves. Ethical considerations become dynamic, requiring ongoing reflection and dialogue. We need to be open to new paradigms that might develop as off-world societies forge identities, possibly quite different from our Earth-based norms. In essence, the idea of enduring human presence on Mars transforms exploration from discovery into a moral venture, an ongoing negotiation with responsibilities, values, and legacy. Each decision today influences the moral fabric of a new civilization, challenging us to move beyond conquest and exploitation towards stewardship. Treating Mars with humility, respect, and responsibility becomes a moral imperative, elevating our role from explorers to caretakers of other worlds. The universe, in an age of permanence and possibility, asks a fundamental question. What kind of explorers, what kind of humans do we aspire to be? Our choices now will shape future civilizations and determine whether we act as reckless conquerors or humble custodians. The potential for lasting settlements elevates our responsibilities from short-term gains to long-term stewardship, pushing us to reflect deeply on moral obligations across generations and worlds. Ethical contemplation must accompany our technological ambitions, ensuring expansion respects the intrinsic value of the cosmos. Every choice we make about exploring Mars echoes back to Earth, shaping the legacy we leave not just in history, but in our collective consciousness. It's more than reaching a distant planet. It's about defining who we are and what we stand for. When humanity sets its sights on Mars, profound questions arise. What stories will we tell? What values will we uphold? And what kind of future are we crafting with each mission, each step into the unknown? On Earth, our space endeavours leave a lasting impact through the technologies we've developed. the scientific horizons we've expanded, and the cultural shifts they have sparked. Think of GPS, advancements in communication, or medical innovations born from space travel's needs. These inventions, conceived for exploration, have become integral to everyday life, transforming industries and empowering millions. Our footprints in space challenge us to think bigger, consider possibilities beyond our planet, and recognize the responsibilities tied to this knowledge. As we push toward Mars, our legacy extends into the cosmos. Every spacecraft launched, rover deployed, and discovery made on Mars showcases human ingenuity and curiosity. These missions symbolize more than tech feats. They embody our collective aspiration to understand the universe and our place in it. Footprints on Mars, from initial structures to future colonies, will stand as enduring symbols, silent witnesses to an era when humanity dared to become interplanetary explorers. They will remind us of our dreams to be a multiplanetary species. But what about the morality of our pursuit? Considering colonization, or venturing there with a potential one-way journey, our legacy takes a new hue. Will future generations see us as pioneers pushing boundaries, or as reckless explorers failing to consider consequences? The ethical issues, environmental stewardship, contamination risks, rights of future inhabitants, mirror our core values. They shape the story of humanity not only as explorers but as responsible beings, aware of the ripple effects of our actions. Our legacy isn't solely about space, it's also about what we nurture on Earth. The drive for Mars has fueled advances in sustainable tech, energy efficiency, and resource management. These innovations can lessen our ecological impact here at home, guiding us toward a more sustainable future. The quest to colonize another planet prompts rethinking our relationship with nature, developing closed-loop life support systems, recycling methods, and conservation practices that could reverse some ecological damage. Beyond technology and morality, the real legacy is psychological and cultural. Human ambition, resilience, and the unwavering urge to explore are woven into our stories. Future generations will view our efforts and sacrifices, whether lives lost or dreams deferred, as symbols of bravery and perseverance. These narratives will form part of our shared identity, inspiring resilience that crosses borders and ages. In space, our legacy also resides in cooperation and collaboration. No nation or corporation owns the cosmos. Shared exploration fosters a lasting legacy of unity. The International Space Station exemplifies this spirit, uniting efforts across borders for scientific progress. Future missions to Mars will need international partnerships, illustrating that humanity's greatest achievements often come through cooperation. Reflecting on our place in the universe, space exploration prompts existential questions. Contemplating our potential as a multiplanetary species makes us consider legacy on cosmic scales. Will we be remembered as custodians of life, carriers of curiosity, or as fleeting anomalies in space's vastness? The answers we write today influence whether future generations see us as pioneers, caretakers, or cautionary tales about hubris. An often overlooked aspect of our legacy is the inspire to aspire effect. Stories of daring astronauts and groundbreaking missions ignite young minds, fueling ambitions in science, engineering, and the arts. These narratives serve as powerful symbols of human ingenuity, shaping values of resilience, curiosity, and hope for generations to come. Through education, media, and culture, we plant seeds that may grow into new explorers and innovators. Ultimately, our legacy on Earth and in space reflects our values and aspirations. Are we environmentally responsible? Are we ethical in our pursuit of knowledge? Do we prioritize collaboration over conflict? Do we see space exploration as a community effort or a race for territory? Our answers will determine how history perceives us. Every step toward Mars is also an inward journey, an inquiry into ourselves. Gazing outward and upward, we seek meaning, connection, and our place among the stars. This drive reflects our deepest desire to evolve, learn, and transcend limitations. The legacy of these endeavours will not only be in colonies or technological marvels, but also in the stories we tell, the morals we uphold, and the future we dare to imagine. It's a story of hopes, sacrifices, innovations, and shared visions. A story that will echo through space and time as long as humanity persists in seeking the horizon. The question of whether humanity should pursue one-way colonization of Mars, regardless of risks, is profound and complex, touching upon ethical principles, existential concerns, technological feasibility, and our collective sense of purpose. It challenges us to consider our core values, our sense of adventure, moral responsibility, and obligations not only to ourselves, but also to future generations and Earth's ecosystem. To evaluate this, we must critically examine ambition, morality, practicality, and long-term implications of such an unprecedented endeavour. Imagine standing at the edge of space, gazing at Mars' reddish horizon, knowing the trip might be indefinite, perhaps eternal. There's an undeniable allure. Humanity has always sought to push boundaries, explore uncharted territories, and ensure survival amid adversity. The appeal of one-way missions partly lies in their potential to establish a new foothold for life, reminiscent of Earth's earliest days when life first took root in harsh environments. For pioneers, this becomes more than science. It transforms into a legacy, a symbol of resilience, curiosity, and the innate drive to explore the unknown. Yet, should this pursuit be undertaken without careful caution and moral reflection? Certainly not. The risks are staggering. Sending humans on a one-way voyage to Mars is more than a scientific venture. It's a moral decision that entails risking lives in a profoundly dangerous environment. Physical hazards, lethal radiation, microgravity's harmful effects on bones and muscles, unpredictable system failures and psychological stress are substantial. The environment offers little margin for error. Supplies of oxygen, water, food, and medical provisions must last decades. Any failure could be catastrophic, possibly fatal. Beyond immediate physical dangers, profound ethical questions emerge. Is it right to send individuals with little hope of return, perhaps driven more by curiosity or national pride than necessity? Do we, as a society, have the moral right to wager lives on a world still poorly understood? The long-term health effects of space radiation, microgravity, and psychological burdens are not fully known, raising concerns about informed consent and our ethical obligation to protect those involved. Every mission would be a leap into the unknown. Failure could result in tragedy not only for individuals but also for societal trust, and such trust supports future exploration. Some argue that one-way colonization is a moral imperative, an extension of our survival instinct, especially considering Earth's finite resources and existential threats. Climate change, overpopulation, resource depletion, and geopolitical conflicts threaten Earth's sustainability. If technological progress can enable a self-sustaining civilization elsewhere, perhaps it's an ethical obligation, an insurance policy for humanity's long-term survival. In this view, pioneering on Mars isn't mere exploration but an act of stewardship, ensuring a future beyond Earth's limitations. However, this perspective raises further questions about identity, morality, and hubris. Are we risking lives for milestones or prestige? Could such endeavours be acts of arrogance, assuming we can tame and colonize other planets without understanding possible unintended consequences? Critics see it as an extension of exploitation, using planets as frontiers for resource extraction or prestige, risking a repeat of Earth's colonial and environmental degradation, just in a new context. The psychological toll on colonists is also critical. Leaving familiar surroundings, family culture, societal support, puts individuals on a challenging, isolated journey. They would face extreme stress, loneliness, and uncertainty, compounded by the risk of medical emergencies with no chance of rescue. The mental health challenges are significant and must be addressed ethically and practically, with robust psychological support systems. The willingness of individuals to accept such risks, whether driven by duty, adventure, or desperation, should be central to moral assessment. Societal acceptance and global consensus are crucial. Would humanity support such a bold, risky step, or see it as reckless? We remain divided over space exploration's costs and benefits. Transparency, honesty about risks, and global dialogue are necessary. Any decision must be rooted in moral responsibility, scientific rigour, and an understanding of the enormous stakes, not just for those directly involved, but for humanity's legacy. Ultimately, balancing human boldness with prudence is essential. Exploration has driven progress and understanding, but must be tempered with humility, recognizing our limits and the moral weight of our choices. We need to consider not only technological feasibility, but also whether society is ethically and emotionally prepared to accept potential consequences. Pursuing one-way colonization could reshape what it means to be human. expanding our frontiers or risking hubris and destruction. This chapter in our cosmic journey demands moral maturity and reflection. Is it a testament to human ingenuity and courage, or an act of reckless hubris? The issue is nuanced, involving hopes, fears, and ethical responsibilities. We owe it to ourselves to approach it seriously and humbly, knowing our choices today will echo into eternity, shaping humanity's future in ways not yet fully understood. It's as much a moral frontier as a physical one, requiring wisdom and clarity. The quest to go to Mars, especially one way, must be driven by responsibility, not just ambition. Only then can our story extend into the cosmos with integrity and purpose. Humanity now faces the possibility of irreversible Mars colonization, supported by several economic models justifying this monumental commitment. These frameworks focus on long-term investment, resource economies, technological innovation, public-private partnerships, and strategic discounting, illustrating how enormous costs and risks can be balanced with potential rewards to create a sustainable off-world future. A core model is megaproject economics, which examines investments in large-scale infrastructure over decades. Historically exemplified by projects like the Panama Canal or nuclear power plants, megaprojects involve high initial costs, long timelines, and complex stakeholder networks. Applying this to Mars suggests early infrastructure, habitats, life support, resource extraction can lead to economies of scale over time. As technology matures, redundancies decrease, and self-sufficiency increases, reducing expansion costs. Once foundational systems are established, further growth becomes more sustainable, forming the basis for an irreversible settlement. Complementing this is the resource-based economy model. It views Mars as a resource-rich hub with extraterrestrial resources, water ice, minerals, fuels, having significant economic value. If processed into commodities for use on Mars or exported to Earth, these resources could spark a boom akin to gold rushes or oil discoveries. Developing a Martian economy capable of generating its own capital could reduce reliance on Earth, making sustainability feasible long-term. Another supporting framework is the technological innovation and knowledge spillover model. Investments in Mars drive breakthroughs in materials science, robotics, energy storage, and life support, technologies that also benefit Earth. Space exploration tends to accelerate technological progress, lowering costs of maintaining colonies and creating new markets. Innovations, initially for Mars, can lead to broader economic gains, fostering industries and resilience. This feedback loop supports permanence, emphasizing that exploration spurs technological and economic growth both on Earth and Mars. Public-private partnership models underpin the case for irreversible settlement. Governments, motivated by prestige, scientific advances, and strategic interests, provide initial funding and policy incentives. Private companies, from resource firms to tech innovators, are driven by profit prospects. Sharing risks and resources enables sustainable long-term development. As the colony matures, private investment could diversify income sources, real estate, tourism, manufacturing, adding resilience. This diversification could make a one-way mission truly irreversible, with the colony functioning as an independent economic entity. Models based on discounted cash flow and net present value quantify future benefits against current costs. These calculations, considering scientific discoveries, planetary protection, spin-off technologies, and societal gains, often show future value outweighs initial investments. Valuing benefits over centuries emphasizes long-term justification for colonization, framing it as a wise investment rather than reckless expenditure. In this view, the economic calculus favors irreversible settlement, as benefits extend far beyond immediate costs. Population growth and demographic models suggest that Earth's increasing population, resource scarcity, and environmental challenges heighten the economic appeal of off-world colonies. Overpopulation, climate change, and dwindling resources create incentives to establish self-sustaining habitats on Mars. These models forecast conditions favoring ongoing investment, viewing Mars as integral to humanity's economic architecture. As Earth becomes increasingly strained, Mars offers a strategic economic safety valve capable of supporting long-term human presence. Morale hazard and legacy investment models posit humanity's survival depends on space colonization as an insurance policy against Earth-bound disasters like environmental collapse, nuclear war, or asteroid impacts. Governments and institutions see this as a collective responsibility, allocating funds toward irreversible investments. Game theory suggests multiple nations or corporations recognize that committing to Mars acts as strategic insurance, encouraging cooperation and permanence. These models support long-term, irrevocable commitments, emphasizing that a sustainable off-world presence is vital for humanity's future. All these models intersect within a broader narrative. Large investments in Mars are not just exploratory, but part of a new economic paradigm. Becoming self-sustaining requires initial risky expenditures that can pay off across generations through resource extraction, technology, and economic diversification. Once justified, the overarching conclusion is that irreversible colonization is both technologically feasible and economically rational. Theories of megaprojects, resource economies, and strategic innovations support long-term human expansion. This is a matter of moral and strategic foresight, committing to a path from which there is no turning back. Governments, industry, and society increasingly recognize that Mars's true value lies in its potential to ensure human survival and prosperity. The economic models provide a framework. With perseverance, ingenuity, and strategic investment, what initially seems impossible can become a lasting legacy. Building a self-sustaining colony may start with bold investments today, but the long-term rewards could secure human civilization's future, making irreversible Mars settlement a rational and inevitable step forward. 747 words. Imagine a world where Mars' crimson plains are no longer silent and unchanging, but alive with human voices, bustling colonies, and a new chapter of civilization rooted on a distant planet. The arrival of a new generation born and raised on Mars would not simply continue Earth's story, but would transform and challenge society as we know it. A key shift would be in our understanding of identity. As communities develop on Mars, members might start to see themselves as Martians as much as, or more than, Earthlings. Borders of nationality, ethnicity, and race could dissolve, replaced by a shared experience of surviving and thriving in a new world, an uncharted territory demanding collaboration, adaptability, and resilience. The sense of belonging would shift. The concept of homeland expands to a planet, with each individual contributing to a pioneering society's identity. This could lead to a re-evaluation of what it means to be human, emphasizing adaptability and communal survival over birthplace or ethnicity. The social fabric of this society would be shaped by life on Mars. Limited resources would make cooperation essential, perhaps more than ever before. Scarcity of supplies, the need for sustainable living, and the environment's harshness would foster social discipline rooted in interdependence. Communities would innovate governance models prioritizing collective well-being, resource sharing, and conflict resolution, crucial in a setting where mistakes could be unforgiving. A culture of ingenuity would emerge, driven by human creativity when survival depends on each decision. Traditional notions of leisure, art, and spirituality might evolve profoundly. Space constraints and environment would influence creativity, leading to symbolic art combining Earth traditions and Martian experiences. New art forms might develop, visual storytelling of pioneering efforts or music echoing loneliness and hope. Spirituality could shift. Without familiar landscapes or cosmic proximity, beliefs might reorient to revere the environment itself. Alternatively, living on Mars could inspire a spiritual awakening, a sense of cosmic kinship extending beyond Earth, fostering philosophies that see the universe as a shared cradle of life. Education and culture would be transformed. Schools might focus on terraforming, geology, engineering, botany, and resilience, training the next generation for space living. Knowledge transfer would focus less on Earth's history and more on forming a Martian identity, an evolving story that each generation carries forward. Rites of passage might include celebrations for milestones like a successful harvest or establishing a self-sustaining habitat, blending tradition with new adaptations unique to their world. Economically, Mars would foster different values. The drive to harness local resources, water, minerals, rare elements, could establish a new economic system, resembling early Earth trades but driven by necessity and innovation. As colonizers developed sustainable methods for food, energy, and manufacturing, a form of capitalism focused less on profit and more on shared prosperity would emerge. tied tightly to environmental stewardship. The fragile, vital balance with Mars' environment would be central. Life's longevity depends on maintaining this harmony. These societal shifts wouldn't be purely utopian. Living far from Earth, cut off from family and natural rhythms, would challenge mental health. Society would need new support: psychological, social, technological. Virtual reality might serve as a bridge to earthly nostalgia, helping maintain bonds across light years. Community rituals emphasizing connection, resilience, and shared purpose would be vital, forming new traditions rooted in Martian life's extraordinary circumstances. Generations on Mars would face ethical issues that shape daily life. Decisions about terraforming, wildlife, and who has rights to be on Mars would define societal norms. Their morality might evolve, prioritizing the planet's preservation over short-term gains. This expanded ethical perspective could foster compassion and responsibility beyond Earth's history of exploitation, guiding societies towards sustainable, respectful stewardship of Mars. The knowledge accumulated, scientific discoveries, technological innovations, would become a lasting legacy. Stories of survival, discovery, and adaptation would redefine human culture, imprinting the idea that humans can thrive far from their birthplace despite adversity. Developing a Martian identity, one forged in challenge and resilience, would serve as a beacon for future explorers wherever they venture next. Ultimately, the societal changes driven by permanent habitation on Mars would transcend mere adaptation. They would redefine what it means to be human amid endless possibilities. A new generation on Mars could become architects of a civilization that unites resilience, innovation, community, and ethics, woven into the fabric of a planet no longer just a distant outpost, but a true home. As humanity prepares to take its first steps toward Mars, the implications ripple through global geopolitics, challenging the established order and urging nations to reconsider shared future endeavors. The quest to reach another planet is no longer just a matter of scientific curiosity. It becomes a symbol of national pride, economic dominance, and ideological influence. Countries race to claim a seat at the cosmic table, driven by visions of sovereignty, security, and status. Some nations see the effort as an extension of their military or strategic interests. The potential for resource extraction, water, rare minerals, or other valuable materials could ignite a new resource scramble, echoing Earth's fierce competition over energy reserves and mineral riches. Control over extraterrestrial resources might confer significant geopolitical advantages, fueling tensions and alliances. Would a single nation dominate Mars, or would coalitions form to jointly govern assets? The fear that space might become a new arena for economic or military confrontation lingers. The high costs of Mars missions also make nations reconsider their priorities. Large-scale space exploration requires huge investments, stretching budgets, and necessitating international partnerships. Recognizing no single country can unlock Mars' secrets alone, many leaders see collaboration's value. International organizations like the UN Office for Outer Space Affairs could play greater roles in fostering frameworks for shared access, governance, and conflict resolution. Still, mistrust and competing interests complicate cooperation. When national pride is involved, compromises are difficult. Disagreements over ownership and rights may overshadow scientific collaboration. Mars exploration could also become a soft power battlefield. Countries establishing bases or showcasing technological prowess will enhance their global influence, shaping perceptions and alliances. Achievements like rover landings, habitat establishment, or human missions may be broadcast worldwide, symbolizing national innovation and resilience. This competition might accelerate technological progress, but risk a space rivalry, akin to a space race redux, necessitating multilateral frameworks to prevent conflicts and ensure space remains a shared human endeavour. Global geopolitics could shift if Mars colonization results in sovereign settlements. Future scenarios might include nations establishing permanent outposts that evolve into autonomous colonies. This could challenge sovereignty norms, prompting debates on jurisdiction, citizenship, and rights beyond Earth. Would settlers owe allegiance solely to their home countries, or develop new identities? How would laws be enforced in off-world settlements? These questions highlight the potential need to adapt terrestrial legal frameworks to space governance, and whether the international community is prepared for this complexity. Beyond legal and political issues, Mars might prompt a re-evaluation of what it means to be a global citizen. As space access expands, the idea of humanity sharing a collective destiny gains traction. This could foster a sense of planetary unity. Conversely, disparities may deepen, those involved in space missions versus those left behind, highlighting gaps in access, wealth, and technological capacity. Such divides could influence perceptions of global fairness and cooperation. Social and ethical debates surrounding Mars missions will influence geopolitics. Issues like the morality of one-way missions, resource exploitation, and planetary contamination could spark diplomatic tensions. Some nations might emphasize principles of universality and peaceful cooperation, while others prioritize national or commercial interests. The rise of private companies in space adds complexity. Who owns rights to discoveries or resources? Questions of regulation, profit sharing, and environmental responsibility deepen, blurring lines between state interests and corporate ambitions. Looking further, long-term human presence on Mars could reshape Earth's geopolitics. Technologies developed for extraterrestrial living might benefit Earth, transforming industries, improving disaster resilience, or fostering new cooperation models. However, detachment from Earth's crises might increase if nations and private actors prioritize Mars over pressing humanitarian or environmental issues at home. This divergence could fracture the global order or create new alliances. The narrative of Mars exploration also influences public perception and diplomacy. Stories of human voyages inspire worldwide dreams, fostering a shared sense of purpose beyond borders. Governments might use this enthusiasm to promote international collaboration. But rivalries may also exploit space achievements as propaganda, asserting superiority amidst divisions. In this evolving landscape, establishing robust, fair international agreements is crucial. The current space law, exemplified by treaties like the Outer Space Treaty, must adapt to realities of sustained presence and resource use. Without frameworks to manage conflicts, tensions could escalate. Thus, humanity must approach space with humility, foresight, and a commitment to peaceful coexistence. The journey to Mars underscores our interconnectedness with Earth governance, ethics, and diplomacy. How nations navigate these challenges will influence our future on the Red Planet and shape global cooperation for centuries. The pursuit of Mars is more than a technological endeavour. It is a profound geopolitical enterprise, testing our ability to unite despite vast unknowns and to steward our collective future across the universe. Imagine a future where migrating to Mars isn't merely an ambitious concept, but a tangible reality, one embraced by those willing to risk their lives for a new beginning beyond Earth. Such a leap would send ripples through Earth's demographics and resource allocation, transforming societal dynamics profoundly and unpredictably. The decision to migrate interplanetarily would reflect human motivations and societal structures. Likely, those pioneering Mars would be driven by ambition, curiosity, and a desire to escape Earth's limitations. However, it would also expose socio-economic disparities. Wealthy nations and individuals with advanced technology would have the means to colonize space, leaving marginalized populations behind. This could deepen existing inequalities, creating a stark demographic divide, a small, privileged class venturing outward, while much of Earth's poorest populations remain tethered to strained, overpopulated areas. Earth's population dynamics would inevitably shift. Some individuals emigrating permanently could lead to a decrease or stabilization of Earth's overall population, easing pressure on finite resources like water, arable land, and energy. Temporarily, this could slow environmental degradation, alleviating urban overcrowding, deforestation, and climate stresses. Yet, the demographic profile on Earth might skew older as younger, able-bodied individuals seek opportunities on Mars, potentially accelerating aging trends and straining healthcare, social services, and workforce sustainability. Mass migration, or the prospect of it, would influence how nations and corporations allocate resources. Governments might divert significant funds towards space infrastructure, building colonies, establishing life support and transportation, possibly at the expense of addressing pressing issues like poverty, healthcare, or climate change. Private corporations could focus on resource extraction, mining asteroid belts or lunar deposits for rare minerals, sparking geopolitical conflicts and competition over extraterrestrial assets. Ethical debates would intensify. Should resources benefit a few or be managed collectively for humanity's future? Technological innovation would accelerate, driven by the race to colonize Mars. advances in habitat construction, closed-loop life support, in-situ resource utilization, and radiation shielding could have benefits back on Earth, enhancing resilience against natural disasters or climate vulnerabilities. These breakthroughs might improve life here significantly. But there's a darker side. Wealth could become concentrated among the technologically elite, widening global disparities. Wealthy nations and individuals might monopolize new resources and technologies, leaving marginalized communities behind and deepening class divides, extending into space. Extraterrestrial resource control could become a core aspect of interplanetary expansion. Competition over mineral-rich asteroids or lunar sites could ignite conflicts reminiscent of terrestrial resource wars, redefining sovereignty and territorial claims on a cosmic scale. If nations or companies claim property rights over celestial bodies, disputes could harden, transforming space into a new frontier for geopolitical rivalry, with Earth's limited resources traded or bargained over amid planetary scarcity and corporate sovereignty. Resource disputes would raise moral questions about ownership and stewardship. As colonies attain self-sufficiency, Earth might be seen as outdated, a damaged environment from centuries of exploitation, worthy of abandonment or exploitation. Alternatively, this drive could promote shared stewardship, fostering international cooperation. Yet human history shows resource scarcity often fuels rivalry, even among allies. Culturally and psychologically, migration to Mars would create a profound divide. The physical distance and technological barriers would foster a split between Earth-based communities and Martian colonists. Over time, separate identities might emerge: Earth citizens versus Martians, with divergent values and visions of humanity's future. This bifurcation could challenge the idea of a unified human race, transforming our collective identity into a fractured mosaic. Philosophically, humanity's self-perception would evolve. Earth, once the cradle of civilization, might become a nostalgic symbol, humankind's birthplace but no longer the primary home. This shift could influence art, spirituality, and worldview, prompting reflection on belonging and purpose. Would colonizers see themselves as stewards or conquerors? Would Earth's environment evoke longing or serve as a symbol of past tragedy, superseded by new worlds? These questions would shape cultural narratives. The broader impact of mass migration to Mars concerns the redefinition of governance and ethics. International treaties, space laws, and new norms would be essential to prevent conflict, promote resource sharing, and ensure equitable access. The challenge is whether we can create a sustainable, cooperative framework or succumb to competition and division. Migration to Mars signifies more than technological achievement. It's a transformative act that could reshape societies, economies, and cultures. While it might alleviate some of Earth's environmental and population pressures, it could also deepen divisions, spark conflicts over extraterrestrial resources, and redefine sovereignty and belonging. The outcome depends on choices, whether space is approached as a shared legacy or further grounds for rivalry. What kind of humanity will we carry into space? Will we foster unity and stewardship or fracture into separate worlds? These decisions will determine humanity's destiny among the stars and the essence of what it means to be human. The debate over establishing an irreversible human presence on Mars involves questions of morality, practicality, and destiny. Advocates argue that human settlement elsewhere is inevitable and vital for our species' evolution. They see Mars as a new frontier, an opportunity to expand, protect humanity from extinction due to environmental collapse, nuclear war, or unforeseen threats. This pursuit is akin to migration out of Africa or the age of exploration, inspiring future generations and pushing scientific boundaries. Proponents believe a resilient, self-sustaining colony would showcase human ingenuity, advancing renewable energy, life support systems, resource utilization, and artificial intelligence, benefiting life on Earth. The idea of becoming a multiplanetary species fosters hope, purpose, and unity, transcending borders. Exploring space is often seen as a moral responsibility, an extension of human curiosity, resilience, and desire to grow beyond our home planet. Opponents, however, raise ethical, environmental, and philosophical concerns. They warn that human activity on Mars could cause ecological contamination, intentionally or accidentally, and fundamentally alter the planet's pristine environment. Once humans establish a colony, Stopping or reversing the process becomes nearly impossible, leaving a lasting footprint. This raises fears of planetary colonization reminiscent of terrestrial expansionism, but on a cosmic scale. Claiming extraterrestrial territory without regard for intrinsic planetary value is ethically troubling. Critics worry that such irreversible colonization might set dangerous precedents, valuing expansion over preservation and risking a form of cosmic imperialism. There are also concerns about global inequalities. Space endeavours demand enormous resources, billions of dollars, advanced technologies and expertise that could be better used addressing poverty, climate change, and conflicts on Earth. Critics argue that investing heavily in Martian colonies might divert vital attention and funds from urgent terrestrial issues. This could exacerbate inequalities, creating a new elite with off-world access, while ordinary populations struggle or suffer. Such priorities threaten to foster inequality and moral discomfort. Why prioritise space when humanity faces pressing challenges here? Environmental risks are central. Mars is harsh, cold, dry, seemingly barren, but scientists debate whether Earth microbes could unintentionally contaminate or interfere with any native Martian life. Once microbes are introduced, efforts to contain or eradicate contamination become nearly impossible. Mars would become part of our human sphere, permanently altered, whether intended or not. Some argue that respecting Mars's pristine environment is morally necessary, and that colonization could irreparably damage its ecological integrity. This could set a dangerous precedent for future exploitation of celestial bodies, driven by economic or political motives rather than conservation. Psychological and cultural impacts are also significant. A permanent presence might transform societal values, fostering stewardship and shared responsibility, or leading to conflicts over governance, resources, and authority. Would life on Mars develop into a new society challenging our notions of identity and morality? The mental health risks, loneliness, isolation, technological failure, are considerable. Colonists might struggle to adapt, with the risk of becoming trapped in fragile enclaves from which return is impossible. Some critics fear that making Earth's outpost essentially permanent could cause humans to lose their connection with Earth, the cradle of life and morality. Earth's resources, culture, and lessons are invaluable. Turning the planet into a stepping stone for expansion could dull our sense of responsibility. This might lead to reckless resource use and neglect of Earth's environmental crises. Space colonization could serve as a distraction, an alluring frontier that diverts attention from the urgent lessons about sustainability, humility, and coexistence. The question of autonomy raises further issues. If Martian colonies become self-sustaining, questions of governance and morality arise. Would we impose Earth's laws, or would Mars develop its own norms? Once established, could we intervene or withdraw? These colonies might become too independent, difficult to control from Earth, leading to conflicts and unintended consequences. The potential for irreversible human presence on Mars ultimately hinges on how we see our future, our purpose, morality, and the kind of civilization we want to build. Advocates are driven by curiosity and hope, seeking to expand human horizons, while opponents see the risk of irreversible harm and environmental destruction. The debate asks whether we are explorers motivated by exploration and innovation, or reckless colonizers risking the unknown. It also raises hubris and humility. Are we ready to take responsibility for another planet's environment? Will balancing exploration and preservation be possible? The decisions now will shape whether humanity becomes a multi-planetary civilization built on careful stewardship, or one that damages worlds beyond our own. As technology advances, the conversation will intensify. Our understanding deepens about risks and benefits, prompting us to consider what's ethical and responsible. The core issue remains: should we pursue irreversible human presence on Mars, and under what conditions? The future depends on our choices. Whether we move forward with respect, caution, and humility, or rush ahead, risking irreversible damage and moral compromise. The debate encapsulates broader questions about human purpose, morality, and our role in the cosmos. It challenges us to reflect on whether expansion signifies progress or hubris. Ultimately, the decision will reveal our collective values and the legacy we leave beyond Earth. Preparing for a one-way journey to Mars involves rethinking our approach to ethics, mental resilience, and technological innovation. It's not just about spacecraft or life support systems, but about supporting, respecting, and protecting explorers as they venture into the unknown. Ethically, the concept of a one-way trip prompts profound questions. We must consider our responsibilities to volunteers choosing a journey with no return. Respect for autonomy is crucial. Every participant must give fully informed consent, understanding risks, outcomes, and sacrifices involved. Transparency is vital. Clear communication about scientific, physical, emotional dangers and societal implications is necessary. Furthermore, we must examine whether offering this opportunity coerces or pressures individuals into choices they don't fully grasp. Participation should be voluntary, free from undue social, financial, or institutional influence. Their decision is both an opportunity and a responsibility, contributing to humanity's progress. We should recognize their courage and agency, avoiding commodification of human life in the name of progress. On a personal level, mental health must be a priority. Mars presents an environment that tests human resilience in unprecedented ways. Isolation, confinement, prolonged separation from loved ones, and the unknown will take a psychological toll. Preparing mentally involves rigorous screening, not only for potential mental health issues, but for traits like resilience, adaptability, and stress management. Pre-mission training should include resilience techniques, mindfulness, coping strategies, and virtual reality simulations exposing recruits to sensory and social isolation. Building a cohesive community, trust, camaraderie, open communication is essential for survival during crises. Establishing a shared purpose, goals, and cultural continuity can support mental well-being. It's also critical to plan for ongoing mental health support on site. Remote counseling, virtual mental health professionals, regular assessments, routines, and recreational activities can mitigate feelings of despair or alienation. Empowering colonists with a voice and decision-making power sustains motivation and a sense of control amidst vast space. While addressing the human mind, technology forms the backbone of this effort. Innovations must prioritize safety, redundancy, and adaptability. Life support systems should be resilient, capable of recycling water and air, producing food from waste, and adapting to failures. Modular designs allow repairs, fostering problem-solving and agency among colonists. Advanced health monitoring and medical technologies are essential, as healthcare on Mars must be autonomous due to communication delays. 3D printing of spare parts and medical supplies ensures continuous operation. Telemedicine can support emergencies, but protocols are needed for situations where real-time consultations are impossible. Robots and AI-assisted diagnostics can aid diagnosis, treatment, and mental health interventions. Research into bioregenerative life support and closed-loop ecological systems becomes a moral necessity, creating environments that sustain life with minimal external inputs. Crops in controlled environments, waste recycling, and renewable energy sources should be perfected before departure. Technological advancements in energy storage, resource utilization, and waste management reduce reliance on Earth, making colonies more self-sufficient. Training must include technological mastery, knowing systems intimately to troubleshoot problems efficiently. Simulation-based training that mimics Mars conditions prepares colonists for technical challenges and helps build confidence and readiness. These simulations can also incorporate psychological modules, helping individuals navigate stress and prevent panic. Interface engineering between humans and machines is vital. Wearable sensors can monitor physical and mental health, alerting individuals and mission control to signs of distress or malfunction. AI can help manage routines, optimize resources, and provide companionship, an important factor considering long-term loneliness. All these efforts require a forward-looking moral framework that recognizes human dignity and rights, even as we push technological boundaries. Ethical guidelines must evolve alongside technological advances, protecting human rights in new frontier societies. Governance issues, who makes decisions in a colony where autonomy conflicts with safety, must be addressed. Ensuring that scientific and exploratory pursuits do not overshadow moral responsibilities to colonists is critical. The journey to Mars, especially if one way, is as much a moral and philosophical challenge as a technological one. It pushes us to our limits: technological ingenuity, psychological resilience, and ethical integrity. To prepare effectively, strategies should integrate respecting individual agency, prioritizing mental health, and developing reliable, adaptable technology. Only then can we honour the brave souls venturing into the unknown, equipped with moral clarity and technological mastery. This venture expands our human story, shaping a future where dignity, courage, and innovation walk hand in hand on the final frontier. It is a test of our values and capabilities, an opportunity to redefine what it means to explore and to exist. We must approach this mission with careful forethought, balancing moral responsibility with technological advancement, ensuring that humanity's reach for the stars upholds its highest ideals. Our success depends on aligning ethics, psychology, and technology in a seamless, integrated manner, safeguarding the well-being and rights of those who will carry our hopes into the cosmos. History is rich with stories of exploration, some driven by curiosity, others by necessity. As humanity considers daring missions to Mars with no guarantee of return, these stories serve as guides, reminding us that every journey into the unknown involves risks, hopes, and lessons about resilience and frailty. The age of exploration in the 15th and 16th centuries offers vivid lessons. Navigators like Columbus, da Gama, and Magellan redefined worlds, yet their journeys were perilous. Ships vanished in storms, crews faced starvation, and some explorers never returned home. These expeditions, driven by a desire to chart new territories and secure trade routes, revealed the profound costs of exploration: personal, cultural, and environmental. These stories teach that exploration is inherently risky, especially when pushing the boundaries of the known. They prompt reflection on whether the potential gains, scientific discovery, technological progress, human expansion, justify the risks. For non-return missions to Mars, where settlers surrender the option to retreat, this risk is even higher. History shows such ventures demand profound preparation: technological, psychological, and moral. Another lesson comes from pioneers in science and medicine, who, despite limited understanding, pushed into uncharted knowledge. Explorers of germ theory or early space missions risked health and lives, relying on ingenuity and collective effort. Their experiences teach us that progress often requires calculated risks, safeguards, humility, and learning from failure. This underscores the importance of humility in Mars exploration, recognizing the universe's unpredictability and unforgiving nature. Historical societal change further informs our perspective. Exploration often led to cultural exchange, conflict, or rupture. The encounters during colonization highlight that exploration can reshape societies with devastating effects on vulnerable populations. Conversely, moments of mutual understanding and adaptation have emerged when explorers approach new worlds with respect and curiosity rather than conquest. Applying this to Mars raises crucial questions. Are we approaching this frontier with humility? Will we regard Mars and potential future inhabitants through stewardship rather than dominion? These stories urge us to consider our moral responsibilities. Going non-return could pose new dilemmas. What rights do explorers hold? What are our responsibilities toward possible ecosystems or life forms on Mars? Lessons from technological and economic ventures warn us against unintended consequences. Colonial exploitation led to environmental degradation and conflict, lessons that resonate today amid climate change and resource depletion. On Mars, resource extraction, if mishandled, could cause harm. Past mistakes emphasize the need for careful planning, transparency, and ethical stewardship, so that our pursuit of knowledge doesn't lead to destruction on Earth or Mars. Personal stories show that journeys into the extraordinary can reshape human identity. When astronauts returned from space, they often described a new perspective: Earth as a fragile, interconnected blue dot. Such moments have inspired peace movements and environmental awareness. For those contemplating a one-way Mars mission, the psychological and philosophical implications are profound. They challenge notions of mortality, purpose, and hope. These stories are not just about exploration, but about how individuals and societies redefine themselves in extraordinary circumstances. The history of exploration also highlights the importance of community and shared vision. The Apollo program, though centralized, inspired millions worldwide. It demonstrated that collective effort and shared aspirations can overcome daunting odds. For Mars missions, this underscores the need for global collaboration among nations, disciplines, and cultures. Especially for a one-way trip, success would depend on a united moral vision, one that transcends borders and individual ambitions. Finally, history teaches us about hope, the human tendency to look beyond current limitations. Explorers set sail, driven by dreams of discovery and salvation. Pioneers facing hardships became legends that inspired generations. Going to Mars without expectation of return could become one such legend, an act of hope, sacrifice, and perseverance. Yet hope must be tempered with wisdom and restraint. Not reckless bravado, but a recognition of our profound responsibilities. In essence, history shows exploration is a double-edged sword. It can elevate us or lead to darkness. Every venture into the unknown requires humility, ethical mindfulness, and an awareness of our interconnectedness. As we stand at the brink of irreversible decisions, missions that could alter human destiny, we must reflect on these lessons. They remind us that exploration is rooted in the human spirit, but must be guided by moral clarity, humility, and respect for the profound responsibilities entailed. As we consider stepping onto Mars, let us carry the wisdom of explorers before us. Let us proceed carefully, honourably, and with stewardship. The stories of those who dared before teach us that exploration is about discovering not just new worlds, but what it means to be human. Accepting the no-return paradigm fundamentally alters our understanding of exploration and risk, revealing deeper meanings beyond practicality. When there's certainty that a journey, to Mars for instance, is irreversible, exploration becomes a profound act of human commitment, sacrifice, and identity. It shifts from a pursuit of knowledge to a moral and existential voyage, challenging notions of safety, ambition, and destiny. In traditional exploration, risk was a calculated gamble, an element to be minimized, weighed against potential rewards. Early explorers faced the unknown with curiosity and trepidation, knowing they might not return but driven by the desire to chart new waters or climb unscaled mountains. Today, space exploration echoes this ethos, yet with escalated stakes. The no-return paradigm eliminates safety nets, no backup plan or retreat. Every decision becomes a moral and existential commitment, requiring new levels of courage and foresight. This shift demands a new understanding of risk as an intrinsic part of exploration, rather than simply something to be avoided. When travellers accept their destiny as permanent settlers, they embrace the full weight of their choices. Risk becomes purposeful, not a barrier to overcome. Living with the knowledge that each day on a new world is irreversible makes risk an authentic expression of human resolve and conviction. This perception transforms our collective view of exploration. Under the no-return model, exploration gains moral gravity, an irrevocable act with profound consequences. It emphasizes not just discovery, but the acceptance of those consequences, that venturing outward entails responsibility. The choice is about intentionally embracing the unknown, fully aware there's no safety net if things go wrong. Psychologically, knowing one's footprint on Mars is indelible makes exploration a lifelong legacy. It creates a sense of permanence, a bookmark in human history, raising existential questions about identity and memory. If you know you will never return home, how does that shape your sense of self? How does it influence your motivations, hopes, fears? These questions intertwine with exploration, deepening its significance.